What do you want to kick us off? Hold on. Let me use my phone. Cool. Ready?
Yeah, ready. Alright guys, welcome to the day 4 of the workshop. So, yesterday, as we know, we tried to build something cool. Because coding is all about finding a problem, and it's not, it's all about solving a problem, no matter what is the challenge. So, do you guys want to pass this microphone around and talk about the issue that you tried to solve and how far you got? It's just like a 20-minute introduction of what you've done.
So me and Shani tried to make something that compares the price of an item in different websites. So we got some help from ChatGPT, and it works. So it will, when you run the program, it will ask you to input the item that you want. So then it will compare between eBay, Amazon, and eBay and Amazon basically. And we try to sub in different websites for like more stores that we can search from, but we are kind of stuck there because some websites doesn't work and we're not sure why.
Yeah, some websites, we run into this in some of our research, but some websites they block like automatic, like bots basically, right? And usually it's like if they're hosted on Cloudflare, they have like very powerful, like these like smiling babies. We run into this issue for like 20% of our articles, but like you run into Cloudflare and then it just blocks you, and then you can no longer use it, right? So some of these like big tech, like market, like eBay or whatever, they're usually hosted on Cloudflare because they can afford it. So that's like I'm not surprised at all.
The problem I tried to solve was creating a program that gets a medical textbook and converts it into a hanky deck. And so I was able to get to the point where it passed the PDF and then created the deck. But in terms of creating the cards, it did a pretty poor job. Like it didn't know what to actually grab. So like I remember one example of an hanky card it made was like, what is this? And it just had a bunch of like random stuff underneath.
Awesome, love it.
I wasn't here yesterday, so didn't do the challenge.
So what I tried to do was, you know how when we do practice questions and like the faculty gives you like an exam paper, they give you like 100 questions, and you need to do all 100 before you look at the answers. Before or not, you're gonna accidentally see the answer for the next question. But I like immediate reward or immediate punishment, so I want to know whether I got it right or wrong before I go on to the next question. So I wrote something to try to split the questions up, so like you get an answer and a question like immediately. But then the way, so I got it to scrape the PDF to pull out all the tags, but I don't know why Monash's PDF is like buggy. All the lowercase I and lowercase t, if they're next to each other and you scrape it, it becomes a capital A and number 1. I actually don't know why. And the same thing happens if you copy paste out of the PDF. So it's not like Python PDF reader's problem. It's more of why the PDF.
Yeah, I mean, I'm sure you might have heard of it, but I was reading about the VCE like stuff that was happening, like on the cover page they put exam questions on that. How do you even do that? Like that's actually quite amazing to do. Like, I don't even know how to do that. Yeah, that's cool. So as you can see, PDF is a really weird format. Like as in sometimes it just like when you try and copy back from PDF, right? Like it's not always like a perfect lossless sort of process, right?
Yeah, but
I don't even know what's happened.
It looks perfectly fine on the
Yeah. Slash, I don't know, like sometimes the people who create the PDF don't know what they're doing, and then it sort of leads to some sort of disaster in the back end. But it looks okay when you get it, right? Yeah. Okay, cool. You're new today, so yeah.
So Donna, Tom and I, we were working on like making a new logbook system instead of Paperpad because Paperpad sucks. And so we didn't get that far. We like got like a database and then asked ChatGPT to do the rest.
Yeah.
And you can so far like add students, add like the tasks and how much they've done, their name. You can like show all students at a table. I don't know if the search function works.
Yeah.
It does work.
Cool.
Because ChatGPT did it. I don't know how it works.
Awesome.
And that was about it so far.
Cool. Awesome. Thanks for sharing.
I work with Eric.
Yeah.
I tried to make something that took the like .fit file that gets stored from a garment and like compares it from the last week.
Yeah.
Like the heart rate and stuff. But I got a bit stuck with trying to like parse out a .fit file.
Yeah. So some of the proprietary like data files, it's just just like you have to use their software, or it's such a specific way that they label it because they're trying to compress it as much as they can. Yeah. So sometimes a bit challenging. But what challenges did you run into?
I ran into was like there were just there was like so many different names for each thing, and then there were so many like unknown data fields because I think it has potential to store so many different variables based on like what watch you're using,
I see.
what
Yeah, cool.
activity
Right.
you're doing.
Yeah, makes sense. Yeah.
For me, because I come back quite late, so I didn't really have a lot of time on this. But I'm just thinking of making a better search machine through like the drive folder, because we have like this Murmurs drive, and because the naming is different for all the files, although they are on the same content, and it's sorted by year. So if I want like specific topic, like maybe upper limb, anatomy or stuff, if I just search upper limb, it may come out like not all the document that is related to that, because some of them the naming is just weird. And we have subject with different name like throughout the years. It's like 3 names for like HD. So if you just search like one name, you can't really get all the notes you want. So I'm just thinking of like really look through all the documents and just somehow use like maybe Cosmos Media or anything to find like the document with the stuff that I really need. Not just by the name but by the content. Yeah, but some of the difficulties are like, first of all will be the format for sure. But PDF, you have slides, you have a lot of stuff, and then the slides, the extension also have different extension for slides. And also I don't want to store the file. I want them just read through and see if this is the file that have the content that I want, but I don't want to have another database that store all the files, because that will be like enormous data set. So yeah, I'm still trying to like maybe just read through without saving all the files. But yeah, right now I can already have like a code to like look through the drive and then return the list of like the file name in it, and without giving out all the subdirectories. So we'll just go in through all the directories and into the file. But yeah, I need to find a way to read through different type of file.
Cool. Were you using any libraries or anything?
Yeah. Because you need like some of the libraries. Okay, the OS, you need to use the OS to read through the files and stuff. And then yeah, actually right now most of the stuff I use just OS, but for like the cosine media and stuff, and reading through the PDF and also reading through slides, you need like convert API to like convert. I'm thinking of converting the slide to PDF to read, because I think it's easier if I turn it into PDF to read it. Because most of them are just words.
Yeah.
My project was to enhance the educational value of case reports. So broad idea is that you can extract, it's like how Nedrum converts their case reports into continued medical educations like CME modules and stuff. So potentially all other case reports have like educational value. So you can like auto-generate like learning objectives, question and answers. I'm trying to email people to ask them if it's a good idea. That's where I'm at. Yeah.
Cool. You should check out, we'll cover it in like 2 weeks or so, you should check out GenStruct, which is like an AI model that you can just paste in text and then it comes up with questions and answers. So it might be useful.
Yeah.
Cool.
The keyboard on my laptop is like low-key broken.
Yeah.
And so like when I type, it is absolutely terrible. So I made a live spell checker, and then I tried to connect it to OneNote through the API, but then turns out that we don't have, I need to pay for that, and I was like, and then I tried to do a PC part like comparer, price tracker, and then I think I came to the same issue where like if I tried to web scrape it, just wouldn't let me, like probably security stuff like that.
Okay, cool.
Yeah, for me, so it was related to tutoring, and I was hoping to get, so essentially like for each student I'd use a different Zoom link, and so I was hoping to be able to track basically all the classes that I do just by like it be able to track when I open a Zoom link how long it's open for, what day it's open, and like which link it is, and so we'll be able to track each student and how often I tutor them, how long I tutor them for, and then at the end of each month it would just add up how many hours I've done, and then I'd be able to send that off to the parents with the invoice. And I asked ChatGPT and managed to like they put something together for me. But the biggest problem that I ran into was that I just couldn't get access to that Zoom data without having like a pro or like business version of Zoom. So then I kind of just got stuck there. But I came across like Open Excel or something it's called, some sort of library that would help me put all that data into Excel and then manipulate it. But unfortunately, you get that far.
I almost wonder if you can use like Mac. Like sure Mac like keeps track of how long Zoom's open, but obviously if you leave Zoom open afterwards or something, then it'll be like, I tutored your kid for 6 hours, but and you're gonna pay for that, like yeah. Cool. Yeah. So yeah, that's also as you're both running into like the APIs is how the companies force you to pay as well, as you're finding out, right? So it's sort of like an avenue for a lot of software companies to make money, right? Yeah. Lucy.
I wanted to make something that meant I would throw out less food. So the idea was to be able to take a picture of a receipt, look at what food is on there, compare that with a matrix of foods and how long they take to go off, and then export as like reminders. But I ended up spending most of that time just trying to set up VS Code.
Okay.
So,
Yeah.
So I didn't get very far in actually making the thing.
Yeah. As you're probably finding out now, like just getting some of the code environments working, it takes forever. That actually takes longer than the actual work sometimes. And even with code, it's already better if you ever get the pleasure of working with hardware or mechatronics. It takes forever to set up the damn system, right? Like a whole day, several days, like a whole team of engineers, like a week even, to set up like all the stuff that happens, right? And even Mac right now, it's already supposed to be easy when you use Windows, and usually with mechatronics, it's all Windows. Absolute nightmare. Like I remember when we were going through our class, like they had someone just basically on 24/7 because we had an assignment that was due, and their whole job was just to help us set up our computer, right? Like that's how bad it was, and it was because it was pandemic times. Like we couldn't access the actual labs, right, where they had already set it up all for us. They spent the whole summer setting it up, and then the pandemic hit, and then so we had to set up on our laptops, and everyone's laptop is different, as you can see here, right? So they had someone literally on just 24/7 trying to fix all these issues that would come up.
So I was working with Mahek, and we were trying to create something that would help us choose a movie we wanted to watch and filter it based on like the actor, ratings, and genre and things like that.
Yeah.
We didn't get too far. We struggled a little bit with exporting the library to the collab workbook, and then from there we were just like going through the file, making sure it was complete, and then that's about it.
Yeah, awesome. So this was actually a challenge from Netflix in 2015, and back that you look at it now and you're like, it's easy to recommend a movie or whatever. But Netflix had this huge data set, right? And they were like, who can create the best recommender system, right? And for obvious reasons, they had a huge financial incentive for it. And they offered $1 million to the team that would best recommend movies or TV shows, right? And we'll actually go through some of it, I think, tomorrow in terms of how the system works, like just a very high level. It's called a recommender system, and like they have discovered all these mathematical tricks to basically really recommend you really well your next movie, right? And they've obviously improved since 2015, and now I don't know, when I use YouTube or Netflix or whatever, it's just like, wow, I do really want to watch that, and so how does that work, right? Like the math behind it is sort of cool, but yeah, like it's really interesting to see that even just in 2015, this was a huge problem, right? Like something you're working on now, it's so much that Netflix was willing to pay like $1 million for it, right? Like that's a huge, I don't know, I think that's a huge amount of money, right? For something that's like a little bit of software, but yeah, really cool to see. You work on the same project? Yeah. Cool. Yeah. Oh, you on that team? Awesome. Yeah, I love it, guys. Like this is amazing. Hopefully we'll get some more time for you to work on your own projects as well, and like whether it's a mini project or even like the last project, just to do something really cool. So we're gonna spend today and tomorrow on neural networks. So hopefully have sort of hands up in there if you've heard of neural networks before. Is it okay? Something maybe familiar with, maybe not. So neural networks are the backbone of how AI systems work. So really sort of key. We're actually going to be going through it sort of slowly, right? So we're going to spend a lot of time. Just please make sure you understand everything that happens, right? So these sort of next 2 days are designed to be on the slow end, just so that we make sure we understand everything really thoroughly, right? Because if you don't understand neural networks, it's sort of like the foundation that builds the house, right? Everything's going to collapse after that, right? And so we want to just make sure that everything makes sense. We have some exercises that are again designed to be really slow, and you just really sort of explore every single part of the neural network, right? And part of the reason isn't just sort of educational, but it's the AI field is sort of weird in that we have all this advanced stuff that comes up, but then someone realizes something really fundamental, right? Like, and it's usually related to the neural network, right? And then that just shifts the field forward, right? And so people who understand the neural network really well are sort of in a good position to usually understand what happens next or even be part of that change, right? And so it's just that's why we've gone through even coding probability in sort of significant detail, right? Because just understanding some of the basics, like even just something stupid like sort of MLE versus map, right? Like it could be that future systems are suddenly based on map, and so you have to understand what that shift looks like, right, and what it feels like even. With neural networks as well, it's a bit of intuition in terms of, okay, we're doing this now, maybe we could do this in the future, right? Maybe someone realizes that this method is a lot more superior for some reason. And so yeah, so we're gonna spend a lot of time on it. And if there's anything you don't understand, please just raise your hand and ask, right? You know, like there's gonna be stuff that might not make sense initially, or you know, needs a bit more thinking. And that's okay if we just literally spend some time thinking about it. So let's just dig into it. So our agenda this AM, and we might actually take longer than this because I sort of planned a day and a half of material. I think it will take actually 2 days though to cover the whole lot. So this is sort of flexible. Is we're gonna go through the very basic problem of regression, right? So neural networks came from regression, right? So we have to understand regression itself. We're then gonna discuss things like loss functions, how to actually construct a neural network, a algorithm called gradient descent, which forms the backbone of another algorithm called backpropagation. Backpropagation is really exciting because this year it actually won the Nobel Prize in Physics, right? So the people who created that in the 1980s, took them 40 years to win the Nobel Prize, right? But it forms the backbone of everything we do. But that being said, you know, people have asked questions, can we improve backpropagation, right? Because we've sort of assumed that it's worked since the 1980s, but I suspect in like 20 years, someone's gonna be like, well, actually we should have done this instead, right? And that's gonna lead to all these insights and sort of a new wave of AI. And then you're actually gonna spend some time working with neural networks and code, right? And sort of really understanding the code, seeing what happens. So let's start sort of from the basics here, so regression models. So hands up if you've seen regression models before. I think it's a maths methods thing, at least when I was going through it. Have you seen it before? Yeah, line of best fit, have you heard of those terms? Cool. So regression sort of broadly is a way to frame a mathematical problem, okay? So it's the sort of like framing it such that you can predict a single output given multiple inputs, okay? So let me just repeat that again. You're predicting a single output. So that is a single sort of answer given multiple inputs, okay? So the inputs are usually many different things. So we'll go through an example of house prices later, right? So it could be like the house size, the location of the house, you know, like, you know, how many bedrooms there are in the house, that sort of stuff, right? And then you're trying to predict the house price, which is a single output. Okay, now later on, we'll actually expand this so that you can predict multiple outputs, right? So it could be, you know, could be binary. So it could be like, here's a chest x-ray. Does the patient have pneumonia? Do they have heart failure, right? So that would be sort of a binary output, like yes or no. Or it could be multiple output, which is sort of a generalization of the binary output, right? So it's like, you know, does this patient have heart failure, pneumonia, or cancer, or whatever, right? Like it's multiple outputs, okay? Now there's the sort of how we frame it mathematically is that we're trying to find the equation of best fit, okay? So for example, in this case here, it's a linear regression problem. We're trying to find the best linear equation that fits the points that we're given, okay? Makes sense? And how we do so is by minimizing an error or loss, okay? Which means that we actually have to define an error function, right? Or loss function, which is how to calculate the error, right? And I mean, you know, intuitively I look at this and I'm like, okay, this sort of looks okay, but if the line was sort of like this, I'd be like, oh boy, like there's something wrong there, right? So intuitively we have some sense of what an error looks like, but we also have to define it mathematically very carefully as well. Now there's many types of regression. So this is, for example, linear regression. There's logistic regression, which we'll talk about. There's polynomial regression. So what if it's like quadratic or cubic or whatever, right? So it's a different type of regression. It's very powerful, but as you see, it requires assumptions. So as someone who's defining it mathematically, right, I need to look at this and go, well, this sort of looks linear, right? So I'm going to try linear regression. Or it might look quadratic, so I'm going to try quadratic regression. But you see how there's sort of assumptions, right? And as you can imagine, as the data gets more complex, those assumptions might be it might be fallible, right? Because I might be making the wrong assumptions. I might be, you know, sort of screw up like the initial assumptions, and then I get a really bad equation, right? And so neural networks, as you'll see later, are very powerful because it removes those assumptions, right? So it forces you to basically just go, okay, here's the data, figure out the function for me. I'm not going to tell you if it's linear or quadratic. You have to figure it out, right?
And so because it removes that, it's become sort of the sort of main method that we do regression now. But you'll see for simple data, you'll still apply something like regression if you know it's linear or you know it's quadratic, because it's a lot faster. It's a lot easier. Okay? Any questions from that? Cool. So let's talk about linear regression itself. So this is a regression model that assumes there's a linear relationship between the inputs and outputs, right? Now, this obviously works well when the data really is linear, right? But it works really poorly when it's non-linear, okay? And so that's sort of part of the fallibility of regression, because I'm forcing it to be linear, and maybe, you know, it's linear here. Like say I only see this first half of the data, right? It's linear for the first half, but then suddenly later on it becomes quadratic, right? And that isn't obvious immediately, right? And so sometimes we might just be collecting the data here, right? For some reason or another. So it could be like a biological thing. We just happen to see this part, and then we don't see this part, right? And we're sort of missing the quadraticness, okay? Now, let's talk about sort of a really simple example, which is to predict hospital length of stay. If you were to predict this, right? Say a hospital sort of reached out to you and they were like, hey, we want you to predict this. What sort of inputs would you have here? So any ideas?
Admission date.
Sorry?
The admission date.
Admission date, yep, sure. As in like Christmas or weekends or something, or what do you mean?
No, so like the specific date that the patient gets like a really fast.
Yeah, maybe because you were counting from zero, as in the 0 point is when they enter, right? Yeah, so it doesn't really matter if they entered like last week or this week, right?
Yeah.
But although there's studies that show that if you enter on the weekend, you're more likely to die and all sorts of stuff, right? Because there's no one around. And if you enter on Christmas, I think it's Christmas, that's another one. And then if people are away at a conference, you're also screwed because there's no one around, right? Like, yeah. Other stuff? The age, yes. What else?
Reason for admission.
Yeah, reason for admission, right? That's a big one. If you're coming in for, I don't know, like some major life-threatening thing, your length of stay is probably either going to be long or very short, right? Because you've died, right? Or if it's something that's just very standard, then it could be very preset. What else?
The equipment, anything of the hospital.
Yeah, okay, yeah. Rural or urban hospital, maybe. Maybe it's really understaffed, maybe it's underserviced. Yep, what else?
Maybe like the treatment that they're getting.
Yeah, the treatment they're getting, the procedure they're getting, right? What else?
Any complications?
Complications, yep, perfect. Comorbidities, exactly. What their past history is, right? Like, have they had previous issues before? Even maybe prior stays, right? Like maybe they've been in the hospital before for the same problem, stayed a week every single time. You know, they're probably going to stay a week. What else?
Like their own housing situation.
Yeah, housing situation. So if you've ever seen in the hospital, a lot of the time it's like the patient's ready to go, but they can't leave because there's not a stable housing situation, right? What else? So you see how you have to rely on your clinical knowledge for this, right? There's lots of different things, right? And we didn't cover all of them. But, you know, I mean, I listed here like age, diagnosis, comorbidities, presentation, medications, right? I don't know what like maybe they're taking some medications that might impact their ability to stay in the hospital, right? Procedures, living state, yeah. So we sort of input all of this, and the whole point is to output this single number, which is how long the patient's going to stay in the hospital, right? Like a prediction of how long. And that prediction doesn't have to be an integer, right? It could be, you know, my prediction is 2.5 days, right? And if they're sort of 2 or 3, then it's like sort of correct, right? And so how linear regression works is that you basically have this output, which is, you know, y, for example, and then you have all these inputs, right? A very sort of long line of inputs where each feature is its own variable, okay? And then you have things like A, B, C, which are the coefficients. And so what we're trying to do is we're trying to find the equation such that this sort of forms the line of best fit, okay? And so A, B, C are what we're trying to optimize, right? We're trying to find the best numbers, right? And each feature is its own sort of input variable. Okay, so that's how we frame linear regression. Any questions from that? So hopefully that's sort of straightforward. So obviously as we get more and more features, this no longer becomes a 2D sort of affair, right? It becomes 3D, 4D, 5D, whatever you have, right? And so as you can see, it gets more and more complex, right? Because you almost have a 10-dimensional sort of equation you're trying to optimize for, right? Can it still be done? Absolutely. It can still be done with linear regression at this point. But as you get more and more data, it gets more and more complex, and it gets really difficult to actually find that equation, right? And then you also need to assume that the relationship between these variables are linear at this point, right? And we don't know if that's true. So you see how we've just listed a bunch of variables. How do we know if one's quadratic? How do we know if one's like cubic for some reason, right? Like what's an example? I don't know, maybe like past admissions, right? Maybe it's more of a normal distribution, right? Because they're centered around the values that they've previously had. You see what I mean? So it gets harder and harder to have that assumption that it's always going to be linear, right? Such that, even for something like age, right? If they're particularly young or particularly old, they're probably going to increase the length of stay, right? If they're sort of in the middle like us, right? Then the length of stay is probably going to be on the shorter end. So even that doesn't feel linear to me, right? It feels like almost like U-shaped or something, right? So the assumption of linearity sort of becomes an issue once you're starting to consider a lot of different variables. So how would we deal with something like categorical data, right? So that's also another big question. Does anyone have any ideas about how we'd deal with, say, whether, so this obviously is fine because it's just a number, right? Like it's a number from 0 to 100 or something. But diagnosis is a yes-no, right? Like it's like this person has previously had diabetes or currently has diabetes. It's a yes-no, right? Does anyone have any ideas about how we'll deal with this in linear regression? Sorry? Yeah, so every diagnosis would have its own variable. And if, say, you were diagnosed with diabetes, what number would it be? 1, exactly. And if you don't? 0, exactly, right? So even just thinking about categorical variables, it's not straightforward, right? Because it's not a number from 0 to 100, right? It doesn't make sense, right? But it's a 1 or 0, right? You either have had it or you don't have it, right? And so this is what is called one-hot encoding, right? Which is, say you have a diagnosis basically for every one of these, or comorbidities for every one of these. You actually label this as 1 if it's true and 0 if it's false. Okay, so even the way that we deal with categorical data can play tricks on this, right? Because it's like suddenly this variable it can either be this or it can be this, right? There's almost no in between. So is that even linear at that point, right? Because it's a 0 or a 1, you see? Maybe it's linear, but it's not continuous, right? Maybe it's just discrete. Maybe it looks like this here and this here. But then you sort of lose all this in between here. And so as you can see, when you consider real variables, linear regression starts to fall apart, right? Because you sort of have this equation that becomes quite complex as 1. But then 2, when you're dealing with just standard things like, does this patient have diabetes? It starts to fall apart because it's no longer linear. Okay, it's no longer sort of a continuous function. Now, what if we know the age might be quadratic? Okay, so for some reason we know the age is quadratic in this function. How would we deal with this? So it's not a trick question. It's supposed to be quite simple, actually. What do we do? Any ideas?
Can you make it quadratic?
Yeah, you just make it quadratic, yeah. It's not a trick question. So what you really do is you just go, okay, I'm going to add, in this case, a square, right? Or it could be n in the general case to that specific feature, right? And then now we can deal with the quadraticness of the age, okay? Any questions on that? Okay, yeah.
When you say age is quadratic, you're talking about like the way that age is used as a predictor of length of stay, or
Yeah.
the distribution of ages?
The first one.
Right?
Yeah. And so polynomial regression is sort of a more general form of linear regression where any of these variables could be pushed to a certain power, right? Now, because obviously of computational reasons, right, you have to define what the max power is in regression, right? So say, for example, we know that it's quadratic for some reason, then you just do quadratic and it tries every potential combination of quadratic. Right now, obviously, if you have more and more variables, then it has to try lots of different permutations of it. If you, for example, know that something's cubic, right, you can try 3 and it's going to take even longer, right, because it needs to try cubic, quadratic, or 1 for all of the above, right? It could be that any variable is quadratic or cubic. Okay, and then if you try 4, then it's going to take really long because it's trying every permutation of it. And so you do have to define as a human user what is the max degree you'd like to go to, okay? So you happen to know that it's quintic or cubic or whatever, you have to define that. But you see how it requires some work on your end, right? And some work that's quite challenging as well, right? Like we listed a bunch of stuff. How do you know if it's cubic or quadratic, right? Like it's really, really difficult. All right, so what if the relationship is not a linear combination, but for some reason you know it's exponential? So how would you deal with this sort of problem? Any ideas? Again, not a trick question, just think back to sort of basics. How would you sort of account for exponential? Any ideas? Yeah, just make it exponential, right? It's not a trick question, so you literally just make it exponential, right? And then if you add the sort of e there, we usually just use e because it's really easy to use in other math, right? It just makes this whole thing exponential, okay? And so this is called a log linear regression, and the reason why it's called a log linear regression is we actually move the exponential to the other side, right? And so it becomes a natural log. And so if you use log linear regression, you basically log transform the output to account for the exponential here. Okay, so this is what's called log linear regression.
So Chloe,
yeah,
you're dealing with each variable or feature individually to begin with?
Say that again, sorry?
Are you dealing with each variable or feature individually to begin with?
Individually. Yeah, so it's individually here, but keep in mind that if you have e here, it could be basically split apart, right?
Yep.
So you could account for it individually as well.
You're trying to figure out if it should be quadratic or linear or whatever. You take your data, you plot it, and you're sort of visually looking at it. Is that the starting point?
Yeah, so you could do that if you have enough data points, right? Which sometimes is very challenging to have as well. And so the best studies would be looking at, you know, age and length of stay. What kind of equation does it look like? And then diagnosis and length of stay. What does that look like, right? Comorbidities and length of stay. But as you can imagine, it's very data intensive, right? It requires a lot of data, requires a lot of analysis time as well, right? And so we've sort of shifted away from it towards neural networks because this is the sort of old method where we took ages and ages to process this data. Yeah. Yeah.
So will these guys, is it assuming that all of them have that same relationship then? Like,
it does, yes.
You can't have like one exponential and one quadratic.
Yeah. So you can do that, right? But it takes a lot of computational power, right? Because you're trying to almost apply different techniques to different variables. And if you think about it, that's sort of what you need to do though, right? Because you can't assume that, it's wild to me to assume that, you know, age, diagnosis, comorbidities, they're all exponential for some reason. Like what does that even mean, right? Like for some of them. And so as you can see, regression is very much a blunt tool. It's just like, hey, everything's exponential, right? Let's just see if that works better than everything being linear, right? Yeah. So, and I'll show you an example later of even a study from 2013, a huge study that we use, right? We still use today even to predict cardiovascular risk, right? And they're using these old techniques, right? And so this is what old clinicians were trained on. And so they sort of still know how to do this really well, right? But yeah, it's a blunt tool, right? So, and you can read these articles now with some skepticism because it's like, is it true that it's all exponential, right? Like that's a huge assumption to be making, right? Okay, so what if the relationship is logarithmic, right? So instead of exponential with logarithmic, then we just apply log to this, right? And so this is called linear log regression. So again, not very complex, right? It's just we're applying these mathematical relationships to each individual variable to get a certain output, okay? So that's just regression. Okay, now what if we say want a binary outcome? So say for example, instead of length of stay, we want to do, is this patient going to die in this sort of stay, right? In this inpatient stay. And so in such a case, what we use is something called logistic regression, right? Is anyone familiar with the logistic function? Have you ever seen it before? It's sort of something that is rarely taught these days, I think. But the function is something that I sort of remember actually as the population function. So logistic regression, or the logistic curve rather, had its foundations actually in modeling populations, right? And you know how we sort of fear overpopulation, right? Which was sort of 20 years ago, we were scared that we were going to run out of, you know, space and that sort of thing, right? So we were actually at this part of the logistic curve, but then as sort of populations grow, right, it peters out, right? And now we're a little bit here, which is we're worried about underpopulation, right? Because people are sort of dying out, right? So yeah, so this curve was historically used for population, but it's also great actually as a binary metric, right? Because it squishes everything to, firstly it squishes everything to a probability, and it provides a threshold where you can say that something is yes or something is no. Okay, so say for example we draw a line across here, right? If the output is above here, then it's a yes, and if the output is below here, then it's a no. Okay, and as you can see, it's obviously not perfect. There are always outliers, right? So we're looking at this graph here. It's the probability of passing an exam, right? Versus the hours that you study, right? So say it's like you spend 1 to 3 hours studying, it's likely that you failed your exam, right? But if you spent like 3 to 5 hours studying, then it's likely you pass. But obviously there are outliers, right? Like there are people who spend almost nothing studying, but they still pass anyway. And then there's people who spend a lot of hours studying, but they fail anyway, right? So again, not perfect, but it is sort of a function that meets really nicely into a binary outcome. Okay, so we use it quite extensively for binary outputs. Any questions on this graph in particular? Yeah.
So it's just that we have all the data points and stuff, and then we use some sort of functions to find like a best threshold.
Yes.
And then we just make it binary.
Yeah, that's even more advanced, right? We don't even do that at this stage, right? At this stage, we just say the threshold is a hard 0.5, right? And if you, for example, get that, then we predict that you pass. And if it's below that, then we predict that you fail. And we're not going to be 100% accurate because there are obviously outliers in both scenarios. Does that make sense? But it is a function that we often use, right? And you'll see it later. It's also called the sigmoid function, right? Whereby it forces this whole equation into a number between 0 and 1, right? And so, sorry, 0 and 1. And so because of that, you can basically use a threshold and then it becomes a binary outcome. So we can predict, for example, that this patient is likely to die or not likely to die, right? And we might be wrong, but it's sort of a way to squish it into a binary outcome. Okay, any questions? Okay, cool. So this is potentially one of the trickiest things we've covered so far. All right, say what if we want a specialized function instead of linear, logistic, any of that stuff. So a very famous equation is the Gompertz-Makeham for mortality, right? So in such a case, what we basically use is nonlinear regression, right? And so regression itself can be applied to anything that's nonlinear as well, right? And so this is actually the graph of mortality as you age, right? And it's a very famous graph, right? And so, you know, when you're first born, your risk of death is quite high, right? But then as you sort of progress through life for the first few years, your risk of death exponentially decreases, right? And then as you age, it sort of increases here and then linearly increases here and then increases right at the end, okay? So this is a sort of really well-validated, well-known graph for death, right? As we age, and as you can see, age is, you know, it's not like it's a linear graph. It looks sort of roughly linear, but there's always this spike at the start, you know, when you just are first born. And so what you can apply in that case is nonlinear regression, okay? So you can basically apply regression to any sort of special equation you'd like. Okay, and so selecting the right model, it's a bit of an art versus a science. You need to always manually inspect the data, right? So like Peter was saying, you need to map out the different variables, right? And then actually see what it looks like, right? It's a very time and data intensive process. You can also check the literature. So it might be that people have said that it's always exponential, it's always quadratic or whatever, right? So you can actually use that as your evidence. And some medical relations have widely used equations, right? And so this is sort of a famous table from the American Heart Association that a lot of cardiologists use. And it's to predict your risk of cardiovascular disease in the next 10 years, okay? And it might be a little bit difficult to see, but they basically assume a natural log equation for lots of different things, okay? So it's, for example, age, natural log of age squared even, right? And total cholesterol, HDLC, like blah, blah, blah. You can keep on adding stuff, right? But this is an equation that they spent years trying to do, right? Like basically on all the data points they could collect in the American population, right? And they mapped out using regression every single variable very carefully, very systematically, right? And so yeah, so this is the sort of byproduct of things like regression, okay? And you're gonna see this everywhere as you go through medicine because a lot of the equations we use are based on regression, okay? A lot of the stuff that you'll see in MD Calc or when you're trying to calculate risk is all regression, okay? So any questions on regression before we sort of move on to neural networks? Yeah.
Because at first, like one of the problem with the regression is that we apply if there's one of the
Yes.
Although some of the data might be linear, but we still treat it as
Yes.
You said that it might be a problem.
Yeah.
The calculation problems.
Yeah.
And stuff. And then after that, you said that we have this non-linear regression. And
Yeah.
why don't we just use non-linear for all, like?
It's because non-linear. Yeah, that's a great question. Non-linear, you still need to apply a known equation.
Or still need to have an equation.
A known like curve style, right? Yeah. So you still need to assume something, right? And that's the sort of fallacy of regression in general. You need to have some sort of underlying assumption on what this graph is supposed to look like, right? And sometimes it's very safe. So, you know, it's if you see mortality data, everyone uses this. No one's going to ask any questions. They're like, yeah, fair enough. You use Compert's make 'em. If you're using something really different, they're going to be like, why on earth aren't you using Compert's make 'em, right? So that you still need to have an underlying equation, even for non-linearities, right? Yeah.
Wait, so like this reminds me of MLE versus MEP. So like this is sort of MLE, right? I mean, in a very like
Yeah.
conceptual
It's still MLE in a conceptual way.
Yeah.
Right? Yeah.
And then like is deep learning like MEP where like
No, deep learning is still MLE, but in a more general sense, as you'll see. Yeah. So neural networks, and we'll see this literally on the next slide, is a more general form of regression that doesn't force you to go, it's this equation, right? So it could be literally anything, right? It could be anything that's even more complex than linear, non-linear, whatever, right? But it's a much more general way to map out equations, right? Which is why it's sort of blown up in popularity. Yeah. Other questions? Okay. So let's move on. So let's discuss loss functions. So a loss function is a quantitative measure of how well an equation fits to data. Okay, so like I said before, you can sort of eyeball it and see and sort of take a look. Like, for example, this is a bad equation, right? But it's obviously very data intensive / graph intensive. You know, you have to be drawing out graphs constantly to be looking at it manually. And when you deal with real data, it's not as clear cut as this, right? You sort of look at the data. I've had to do this before. You look at the data and you're like, is it linear? Like you're trying to convince yourself it's linear, but it's not linear and you're not sure, right? And so it's an absolute mess, right? And so what we need is hard functions, hard math that says this fits well, this doesn't fit well, instead of sort of eyeballing it, right? And we'll talk about this later, but we are trying to minimize this loss function later, right? Through a algorithm called gradient descent. Again, we'll cover that later. Now, any ideas on what a loss function could look like? So say you were given this task of somehow quantifying how poorly or how well this equation does. What would be some ideas about how to do that? Yes, so squared distance from the line. So for example, say we have this line here. You can calculate the distance between the line, which is our prediction, and the real data, right? So you, and why do you square it? Yes, exactly, right? So even if I were to calculate, you know, say this line here minus this, right? It would be a positive value because we're getting the line minus the dot. If I were to do the opposite, right? So the line minus the dot, it would be a positive value, right? Or sorry, a negative value. And so because of that, it starts negating out, right? Now, instead of squaring, what's other ways to negate out that negativity or positivity? Sorry? Yeah, I mean, you could absolute it, right? You could absolute it as well, right? Now, what's the difference between absolute and squared, though? Yeah.
Like the derivative at 0 is like, it's like discontinuous, isn't it?
For the absolute?
Yeah,
exactly. Yeah. Although you never get perfectly 0 anyway with real data, right? So you're not too concerned about the derivative being an issue at 0. What else? Which has bigger values? Yeah.
Is it the one where it punishes the
Yes.
incorrect one?
I mean, is it the squared one or the?
The square.
Yeah, the squared one is going to punish it more, right? So let's talk about what that means, and we'll go through the equations very soon. But say you have this line here minus this dot, right? Say it's a value of 1.5 or maybe 2. Let's just do 2, right? It's easier math. If you take the absolute, the value is 2. So it tells the model the loss is 2. Hey, you've screwed up by 2, right? But if you square it, then it tells the model that, hey, you've screwed up by 4, right? So it punishes errors a lot more heavily, right? And so it's almost a bit of a philosophical question. How heavily do you want to punish this model, right? And it seems to be that we've landed at the squares, and we'll talk about that later, okay? So mean squared error, which is the name of that error, is a very commonly used, we use that everywhere, right? You're gonna see it everywhere. Okay, so let's go through. So even before that actually were some more basic things that I was thinking about, right? So sort of naively, I was like, can we use correlation, right? So correlation is a metric of how well correlated the line and the values are, right? But let's take a look at what this actually means. So recall that correlation, in this case here, you have a strong positive correlation. This would be considered a weak positive correlation, right? So you see how the line sort of closely matches the points for the strong one and then poorly matches for the weak one. You can also use correlation to define whether it's a negative or positive correlation, right? And so correlation is something that was considered sort of in the history of machine learning as well, right? Now, one of the reasons why it isn't used is that it sort of only accounts for one input variable, right? And recall that we need multiple input variables, right? When we're dealing with, for example, length of stay, we rarely want to just use one variable, right? It's also not very differentiable, right? So this is not easy to differentiate, right? And so because of that, people don't like using correlation. We need something that's very easy to differentiate. And you'll see why later, because in gradient descent, we need to differentiate this loss, okay? So at some point, we need to differentiate this equation. Another sort of equation that was considered in the history of things was R squared, right? So R squared is a little bit more complex than correlation. You don't sort of really need to know it. Hopefully you've seen it though in medical practice, right? But it's a measure of how strongly the variability in the output variable can be explained by the input variables, okay? Again, not very easy to differentiate. Okay, so when you look at this equation here, it's practically impossible to differentiate. And so because of that, we don't use it either, okay? Now this is the magic bullet that we ended up using because it's very straightforward to differentiate and very easy to use and intuitive to understand as well. And so it's called mean squared error, and it's quite a simple thing. So whenever you see this equation here, right, this is the real ground truth, and this is the model prediction. Okay, so I just sort of imagine, you know, the predictor, it's like sort of like a wizard, it wears a hat. Okay, so y hat always means that it's what the model predicts. We then minus it, that's called the error. We square it, and then we calculate the mean. Okay, so a very sort of simple formula. Now the square turns all errors positive, right? So we don't have to worry about the negative and positive side of things. And it penalizes larger errors more. Okay, so if, for example, the model screws up, it's really going to take that into account. Okay, and the more it screws up, so say it screws up by like 2 versus 3 units, right? The error is 4 versus 9. Okay, so it's a huge amount of error to the model. And so we've found this sort of as a happy medium, right? Like could we cube it, could we, or not cube it, but maybe quadratic it, right? When we quadratic it, it's too much. The model gets sort of like too punished for what's happening, okay? So square is a sweet spot. Very simple, very differentiable. So again, very sort of straightforward function. So let's actually give this a try. So maybe work for about half a minute to see if you can actually calculate the mean squared error of this. Okay, so this column here is what our model is predicting, and this is the ground truth. Okay, so again, it's not a trick question. See if you can just apply the formula to a very simple example. Okay. Does anyone have any suggestions about what the MSE is in this case? Sorry? Okay, do you want to explain how you got there?
We just find the difference between 5 minus 4
Yep.
squared and plus 12 minus 10 squared plus 7 minus 14 squared, we have 54, and then divide by 3.
Yes, perfect. That's it. Okay. Any questions? So again, very simple. Okay, it's not supposed to be sort of complex math, and that also leads to very simple functions that we can differentiate later. Okay. Now other metrics also exist, right? So I was talking about instead of squaring, we could use absolute, because the absolute also sort of deals with the negate effect, right? Now, what would be the trade-offs of this? And we've already discussed it. It's easier to interpret, right? So when you're looking at the error, it's a much more direct mathematical calculation, right? Because you're not squaring things. But the model becomes less sensitive to errors, right? And so people also experimented with this for some time. So this is, again, was the research avenue in the 80s and 90s, right? But they decided that the model wasn't learning fast enough, okay? So you also potentially see this out in the wild. I haven't seen it that much, but if you see it, sometimes it means that the model was too sensitive or something, right? Like there was some sort of issue that they had to correct. Now, another sort of idea that has become very popular recently, so it's a very, very old formula, but it has become much more popular recently, is considering errors in a polar way. Okay, so we've been talking about Cartesian coordinates this whole time, right? So in this case, they're basically using more of a polar system whereby you have, for example, x and y. If they're close in a polar sense, then it's less error. Okay, and if they're further away, then it's more error. In what circumstances would this actually be useful? Any ideas? Yeah.
If you want to add two variables and relate it to each other.
Yes.
Similarity.
Exactly. Right. So this is a formula called cosine similarity, right? Cosine just obviously meaning the angle between the two vectors, right? And we actually use it a lot for language, right? And so when we deal with transformers, which were created as a way to deal with language, right? You actually see cosine similarity quite a lot. Because how we can map language, and I think I talked about it on Monday, is you can basically map language in 3-dimensional or 4-dimensional whatever space, right? Whereby concepts which are similar to each other are closer to each other, right? So for example, it's like tutor, student, university, it's sort of here, right? A banana is here. So you can actually map out using polar coordinates how similar these concepts are. Okay, and that's where a loss like cosine similarity is very key. Okay?
Sorry, just to clarify, so that's used in loss, right?
So yeah, so it can be used in loss, right? Yeah, if you're trying to minimize some things, but it can also be used to detect how similar certain things are as well. Yeah. Okay. All right, perfect. Okay, so let's get started on the first exercise. So in this case, we're going to explore regression a little bit. So if you go to this link here, you can work in pairs or groups of three or whatever you'd like, really. I don't really mind. But run through those exercises, and I'll give you some time to work through it. Let's just see how we go. Got the link? One? Yeah. it's recording. Cool. Yeah, so hopefully you had fun with the regression problems. You can hopefully see sort of the issues of regression in general, which is this sort of big assumption here about whether it's a linear or polynomial model, right? So you see how like it's obviously a big responsibility to be selecting that. And so yeah, so as you'll see later, neural networks sort of provide you the power to avoid that altogether, right? So it's sort of a very powerful technology. Now, a couple things that are sort of useful to discuss. Did anyone sort of notice how the coefficients blew up as soon as you tried like degree 2 or degree 3, right? And then I don't know if you maybe tried up to degree 10, but it started like crashing the whole collab, right? And did anyone sort of figure out like why the number of coefficients blew up? Yeah.
Is it because like if you put in like when you use the polynomial, it gives like different features more functions for each features.
Yes.
So it's not only like one value, it's like maybe x squared, x, and then yeah, so you have like 3 coefficients there already for like 1 features.
Yeah, exactly. So I mean, if you looked at the house price like document, right, there's many features, and so it's talking about the coefficients of every permutation, right? So every potential combination of features, right, up to squared as well. And so for example, you know, it could be the latitude plus the longitude, then the latitude plus the number of people in the house, or latitude plus whatever, right? So it's just providing you coefficients for all of that, right? And it's also useful in another sense, which is say you have a lot of medical data, you know, you want to figure out like what coefficients are really important or what variables are really important. You want to take a look at how big those coefficients are. If those coefficients are near 0, then it means that that combination isn't really important. But if the coefficients are really high, then you know that that combination of features is really important, right? And so it's also useful just say if you have a lot of medical data, you want to figure out risk factors, or you want to figure out, you know, causes of something, right? Like causes of length of stay to increase, then you'd be looking for high coefficient variables, okay? So again, just another sort of useful tool to have in your toolbox. Now, did anyone sort of see the loss as you increase the number of degrees of your polynomial function? Did anyone sort of experiment with that? So what happened?
It went down.
Sorry?
It went down.
Kept on going down. Kept on going down, right? Do you have any theories as to why?
It models it more accurately, I guess.
Why?
Like degrees. I don't know. I guess the curve could fit it better.
Yeah, exactly, right? So say we had sort of like a series of points here, right? So say you have like a sort of linear line. So it'd sort of be like this, right? So you see how with sort of 1 degree, you really can't capture that much complexity in the data, right? Fair enough. And then if it's, say, quadratic, then it'll look like that, right? So you can capture a little bit more complexity. If it's cubic, then it looks maybe like this, right? But then say like if you increase it to 10, or maybe 4 or 5 or whatever, you start getting a curve that sort of really, and this is like the steadiest of my hand, but really captures the points, right? And so when you're trying to calculate the error, obviously the error between, you know, the line and the point is really small, right? Now, does anyone sort of have an idea as to why this is a bad idea and why we don't just keep on increasing to 100 or 1,000? Yeah. It overfits. So this is a problem in machine learning that is the bane of your life later on, which is the model can overfit, right? So it really fits to the points that you give it. But then as soon as new data comes in, so say this new data comes in here, if I had done a linear thing, you know, like this, then it would have done okay, not too bad, right? But you see here, like now, because I've got this really, really fancy sort of curve going on here, it could do really poorly, right? Like the prediction that it has is up here and the real point is down here, right? So this is a problem in machine learning called overfitting, and there's actually lots of techniques to deal with overfitting. But as you can see, this is why we don't keep on increasing to like hundreds or thousands, because it really perfectly matches the data that you give it, but not much else, right? And so conceptually, it's sort of like seeing, you know, like a male have an AMI and thinking that only men can have AMI, right? So you only fit really to the data you see, okay? So that's called overfitting. All right, so let's move on to the next section. Okay, so let's start discussing neural networks. So when we had sort of this linear regression problem, we could represent it as a single layer neural network, right? And that was actually called the perceptron. So someone just realized that, hey, I could sort of put this linear regression problem in a graphical format. right? Like I think it was 1983 or 1985 when someone just decided to do that. And how that sort of works graphically is you have these inputs here, which are your features. So X1, X2, X3. So for example, it's like, you know, comorbidities, disease, age, whatever you have. And then you represent the weights as these lines here. Okay, so the coefficients, as weights, which are represented by these lines here. Okay, so you just basically go, okay, W1 is the coefficient for our feature X1. W2 is the coefficient for our feature X2. And W3 is the coefficient for our feature X3. Okay, so it's just, again, it's a graphical representation. We then also need to account for the y-intercept, right, in this as well. And it's not represented graphically, but you always have a y-intercept, right, which is where it actually starts when everything is 0. And that's also known as a bias term. And so then when you sort of combine this linearly, so very similar equation to what we had before, then you get an output, which is y hat. Okay? So again, this is just a graphical way to represent a linear regression problem. Okay? Nothing else sort of special there. Now, a couple of other terminology. So the W1, W2, W3, which are coefficients, plus the bias term or the y-intercept term, are called the network parameters. Okay? So it's just the parameters of this neural network that we have. When we say weights, we usually include biases as well. Okay? But you'll sometimes see it called as weights and biases. Okay, so that's it. So it's really just a graphical representation of a linear regression model. So nothing special. Now, why is this abstraction useful? It allowed us to expand how many layers we have, right? And start to get a lot more complex functions. Okay? So as soon as, you know, someone was like, hey, I have this single thing here, 3 years later, someone was like, hey, what if you stack another layer? Right? And you know, 3 years is a long time. I think it was like 83 to 86 when someone finally realized, hey, you could stack another layer, right? And that was a huge sort of moment in the field. And so what's sort of cool about this is it enables us to model composite functions. Okay, so you have sort of a linear function here, and then you have another linear function here. So again, very sort of powerful recognition, right? Because now you have composite functions, right? And if you recall, composite functions are is like f of g of h. Do you remember all that stuff from maths methods, right? So that it just allows us to sort of model multiple functions recursively, okay? Now, some terminology sort of came out of this phase, right? Which is the depth, which is the number of layers we have. So in this case, we have a depth of 2. Sometimes people might call this 3 as well, right? So you sort of see both ones. So this is 2 or 3 depth. The width is the highest number of neurons in any layer, so the width of this is 3. Okay, so because we have a 3-3-1 architecture. And then when we sort of combine the, the features with the coefficients, recall that our function sort of looks like this, right? Where it's like each individual coefficient is multiplied by the individual features, right? And does anyone sort of recall what that is in maths? So it's the dot product. Okay, so recall that we have 2 vectors or matrices or whatever, and you're trying to get the dot product of the 2 vectors. Okay, so when we say, for example, Wx here, it means it's the dot product between the weights and the values we have for the features. Okay, so just to sort of represent this mathematically, h in this case is equal to W1, which are all the weights here, multiplied by x, right, which are the features here, plus the bias term. And then y, or y hat rather, is equal to W2, so the weights here, multiplied by our hidden layer, plus B2. Okay, so again, very simple mathematically. Okay. These here also represent the matrices for our weights, so we can actually put W1 into matrix form here. And then they just basically represent the pairwise weights between each individual sort of node there. Okay, so for example, that will have a weight, that will have a weight, that will have a weight, that, and then that. Okay, so you get 9 weights. In this case, you'll also get 3 bias terms, right? So each sort of value here has a y-intercept that you need to account for. And then in this layer here, you only have 3 weights. Okay, and then it has a bias term for this whole layer here. Okay, does that make sense? Okay. So what would this equation look like if we have a 3-layer network? Okay, so just sort of think about that in your head. What would this sort of look like? Any ideas? So how I sort of think about this? Yeah. Do you want to?
You just like put another like kind of linear equation.
Yeah, exactly. It's not complex, right? So it's like this could be like h1, for example, right? And then this would become like h1 here. This would be h2, and then you sort of add like w free plus b free here, right? So it's another sort of simple equation.
Sorry, can I just clarify? Why is it that the first input layer has 3 biases, but then the hidden layer only has 1?
Yeah, so the reason why is, so this one here is, it's a bias. Maybe it's actually easier if you think about it from an output perspective, right? So the fact that you have sort of this set of free here leads to one bias term. So for this one here, you see how it's like one set of free, one set of free, and then another set of free. So that leads to 3 bias terms. Yeah, it's to do with the way that it's connected to the output, right? Yeah. You can visualize it sort of any way, but I think it's easier if you do output. Yeah. Okay. But yeah, so as you can see, when we expand to 3 layers, it's simply another sort of linear equation, right? And then 4 layers, it's another linear equation. So you can see how you can sort of scale this very easily and becomes just a bunch of linear equations where you're doing composite functions constantly. Yeah.
Just a question on the bias as well then. So like, would you envision it to be like linked to the actual layers itself? Because if you're adding, so like the bias for W1 would actually be sort of like a property of hidden layer 1.
Yeah, that could be one way to visualize it, right? It just depends on whichever way sort of works more easily for you.
Okay, sure.
Yeah. Other questions?
So
yeah.
It's just like you have a lot of different bias in W1, different bias from like H1, another bias from H2, another bias from H3.
Yeah.
Just you have a list of bias from like list of output.
Yes. Other questions? Okay. So far what we have are a set of linear equations, right? And as we've learned, if we use linear equations, then we can only really model linear functions, right? So what do we do if we want to model nonlinear relations? Any ideas? So again, not a trick question, right? So what you do is you basically add a nonlinear function when you're dealing with the weight times the features. Does that make sense? Okay, so this is actually a really important realization because initially, all this is linear, right? Which means that the only equation you can model, so the only equation that comes out of this has to be linear, right? Because at no point do you add anything nonlinear at all. As soon as you add a single nonlinearity to this, right, it means that this neural network can now model nonlinear things. Okay? A sort of very important point to make. So we'll discuss what this function could be. There's actually multiple options, right? And it's called an activation function, right? And the activation function is actually inspired by biology, right? When neurons, when they add up like the action potential, sort of like, the action potential, that's called an activation function, right? And so this is also inspired by that. It's also called an activation function. Okay, so as soon as you sort of add this nonlinearity to all of these nodes, this becomes a very powerful tool to model nonlinear interactions. Okay, and what's sort of interesting is that for this nonlinearity, and you'll see the sort of tricks that we use, we don't need to define if it's quadratic or cubic, which are still linear, or exponential or logarithmic or whatever, right? We actually use a very simple function to force nonlinearity. Okay. So this goes back to a theorem called the universal approximation theorem, right? Which is a really important theorem in machine learning, which basically says that a 2+ layer neural network can approximate any continuous function if you have a nonlinear and suitable activation function and enough width. Okay? In other words, neural networks, as soon as you introduce a nonlinearity, right, like a nonlinear activation function, they become a general purpose method that can approximate any continuous function. Okay? So if you take a look sort of graphically here, if you have a small neural network, so say this is the real sort of line that you need to model, right? This sort of step function thing here. You see how if you have very few neurons, then it approximates to this, right? If you add more neurons, then it gets to this. And if you keep on adding more neurons, eventually you manage to get a function that can approximate what it looks like. Okay? So sort of very powerful set of techniques. And again, another example here, when you start with very few neurons, then you see how it sort of guesstimates that this is what the graph looks like, right? But then when you add more neurons, then it can predict what this looks like with fairly high accuracy. Okay? So neural networks, again, they started off as a sort of way to graphically represent linear regression, but then that allowed us to actually see that you can model any nonlinear thing and not have to rely on defining what the function is. Okay? Very, very powerful stuff. So let's talk about gradient descent. So far you haven't sort of seen this part yet, right? But when you sort of provide a function, the sort of function, the error, right? Like the mean squared error or whatever, it's trying to minimize that error. So let's discuss how that actually works, right? So recall the purpose of regression was to find the underlying equation, right? So that you could predict, or best predict, a single output given multiple inputs. This is still the same goal for neural networks, right? We've just sort of found a new way to graphically represent it. Now, how we actually do this is through a method called gradient descent, and it's really simple. It's basically saying that, say we have a 2D graph like this, right? Say we have only a single input, right? Where we have the weight or the coefficient, right? If we actually slide that coefficient along, so say from -5 or -10 or whatever to +10, you can map out what the mean squared error is, okay? And so say, for example, the mean squared error might decrease like that, it might increase at this point, and then it might decrease again, right? And then increase, decrease, and then increase, right? So this can often be sort of like almost a landscape, right, that we can look at. Now on that landscape, basically what this means, and this graph here isn't a 0 point, but it's rather just for educational purposes, you can basically have a point where the error is the lowest it will ever be. Does that make sense? So that mean squared error is as low as it's ever going to get. On the converse, you'll also have a point where the mean squared error is as high as it's going to get, right? So that is the model's doing extremely poorly. Okay, it does really well here and extremely poorly up there. And then sometimes you might have points where it does sort of well locally, right? But it's not the global minimum. Okay, so it does sort of well here, but it could do better if you happen to find that. There are also points where it could do really poorly, but it's not as bad as it can get. And then there are lots of points sort of in between, right? And so, again, we looked at this graph and we realized that we could actually map it as a landscape in our heads, right? And so this is what happens if you have one weight or one feature you want to optimize for. But say you have multiple sort of features, then this is what it looks like, right? It becomes sort of like a 2D landscape, right? So again, a sort of very useful visual representation to always have in your head, right? And again, this is a simple, sort of very simplified version. You have one input feature and then a second input feature, and this is what you get, right? Where the mean squared error might be really low if you can find these regions here, right? And really high if you're sort of operating around here or here. So that is the model predicts really, really poorly, right? And so using sort of this visual representation, we created an algorithm called gradient descent, right? Which is you're trying to go down the gradient of the loss landscape. So you're basically just going downhill until you find the lowest possible point. Okay, so I always imagine this sort of as a hilly landscape, right? And I'm just trying to find the lowest valley. Okay? Any questions on that from a conceptual standpoint? Yeah. Yeah, correct, yeah. So that's, if you just sort of ignore the fact that it's negative, you're right, it should always be positive, right? I just couldn't find a picture that was always consistently positive, yeah. Other questions? Okay. So if we go back, gradient descent essentially minimizes the loss function by iteratively moving in the direction of steepest descent. Okay, so let me just repeat that. it basically looks at the gradient of where you are, right? So it differentiates at the point in which you're standing right now, and then it follows downhill, right? So for example, the gradient is positive, you go the opposite way. If the gradient's negative, then you keep on moving in that direction, okay? So again, let me just explain it in a slightly different way. Say the coefficient you have right now is at 2. It's just like randomly you've selected 2, right? You differentiate at that point, right, for the loss function, and then if it's negative, you move it up to 3, right? And if it's positive, then you want to go backwards, so you move the coefficient down to 1. Okay, so it's a very, very sort of simple concept, right? You're just differentiating, you're seeing which direction is downhill, right, which is the negative gradient, and you're going down there. Does that make sense? Okay, so again, a very simple concept, right? You're just really sliding the coefficient in the direction of the negative gradient. Okay, that's all gradient descent really is. Okay, so what should be our initial weight value? So say you have absolutely no information about the problem that you're tackling. How should we decide our initial weight value? Any ideas?
Random.
Sorry? Random, yes. So one great idea is random, and we actually do use random quite a lot, right? But what's the issue with random? So say we start here, right? And we'll go down and find this. Say we start here, and we're very lucky, we start here, and we'll go down and find the global minimum. If we start here, we'll find this, right? And so as you can see, it's there's sort of issues no matter where we start. And so random is the best thing, and sometimes you randomize multiple times, right? You just randomize multiple times, and then you see where you end up. And sometimes you're very lucky, and you'll find the global minimum or something that looks like the global minimum. Yeah?
That's going to sound like really random, but can you start at like a maximum? If you start at a maximum, your gradient's 0 bucks, you're cooked.
If you start at a maximum, so you never, remember precision, right? You never start at exactly the maximum, right?
Right.
Even for precision, yeah, exactly that point, because it's probably like, 245.1386745 or whatever, right? You never start at exactly that. The probability you'll start at the exact global maximum is near 0, right? It approaches 0.
Otherwise, you can't really move. Can you really move if you're like, how do you know which direction to move in?
Yeah. I mean, look, if that's the case, sometimes it's, you start at a, like a little divot here, right? That, in which case you just need to randomly init again, and then you'll be lucky and you might start there instead, right? So if you're doing really poorly, you just randomize the model, like start from scratch, scrap the model, and just start again, right? Yeah. Other questions? Okay. So, it's just what I was demonstrating before. If we start here, then we might get lucky and find the global minimum. We start here, we might end up sort of going left or right? And so the answer is to randomly init and do it multiple times, right? Sometimes you might just end up, here and you're unlucky, right? Or you might end up here and you're lucky. Now, part of the issue as well is that when we're looking at this landscape, we actually don't know where the global minimum is, right? Like, how do you know that, like down here, there's not like some giant minimum there? You don't know. There's no way you can know, right? And so that's why random init also helps in that you start like completely randomly somewhere in the landscape, right? Now, like I said before, if we have 2 weights, this is what the landscape looks like. This is the thing that everyone keeps in their head. Like every sort of machine learning or AI engineer, they always have this image in their head because you need to sort of imagine yourself finding the values of this landscape, okay? Now, what if we have 3 variables? It's actually quite hard to represent, but this is what it looks like, okay? And even before, we were dealing with house prices and we had 10 variables. I don't even know what that looks like, right? Like what 10 variables literally looks like. We can't visualize it because we live in a 3D space, right? And so this is called the curse of dimensionality. As you move up the number of variables you have, right? And some of the models we have now probably have millions or billions of variables, right? It gets harder and harder to imagine and what that landscape looks like, right? And find the global minimum. How on earth are you going to find the global minimum in this, right? And so just stick to this one, okay? Just stick to this one in your head, right? Like this is a lot easier to imagine, right? Even though really you're operating in this, okay? And you're operating in something probably even more complex because you likely have more than 3 variables. Okay, so sort of a recap on gradient descent. is to consider your current position, find the steepest negative gradient, take a step, and repeat. Okay? So mathematically, how we sort of represent this is we have the old weight, which is where we're standing, and then we take a step, which is represented by this alpha, right? And there's a whole sort of science behind what step size we should even take, right? If you take, for example, too big a step size, so say we're giants in this field, and we take too big a step size, we might end up here, right? If we take too small, then what's the issue? We end up taking way too much time, right? If we take too small, it could be like, we're just moving little bits, right? And it's going to take forever for us to find the value, okay? So even the step size is something that people really have to consider. And then you basically take a step in the direction of the loss gradient, which is we differentiate the function where we are, and then we take a step down the value, okay? And if we're going uphill, then we know that we needed to turn back and take a step in the other direction, okay? Any questions about this? Okay, so again, a very simple formula, and you're hopefully familiar with the assign operator by now, which is in Python just the equal sign, right? Remember, if we want equality, then it's two equal signs. So assign just basically means that check the old weight, take a step in the direction of the negative gradient, and then update our weights. And when we just keep doing that over and over again, right? Potentially even millions of times. Now, a little bit more about the math. So these W's here are a vector for all the different weights that we have, right? And it could also be a matrix as well. We take a step, this alpha means the step size, and then this loss gradient is the partial differentiation of our loss by each individual weight, okay? So what we're really doing is we're actually differentiating on a per weight basis, and then we take, like say we have two weights here, so we calculate the gradient this way and that way, and then we take a step that way in the middle. Okay, so that's basically all that's saying. Now how to calculate DLDW, it's basically just the chain rule where we use the y-hat predictor as the sort of middle variable that we need to use for the chain rule. And so these functions here are just based on, the first is the loss function, so that's why we needed a differentiable loss function. And then the second is the linear regression function, which is generally quite differentiable. Okay, so again, you don't need to dive too much into the math of this. It's just sort of the reason why we need differentiable stuff. Okay, so all the stuff we sort of need to use, all the math we need to use, needs to be simple enough and differentiable. Okay. All right, so let's talk about step size. So this is, it's been a headache for like all machine learning engineers for quite some time, and people have philosophies about it and all sorts of stuff, right? So let's just talk about what this means. So it's how big your steps are. So if we imagine a sort of 2D example, if our step size is too big, then you see how it takes quite some time for us to get to the bottom, right? And this is a good scenario. If we're very unlucky, it keeps on going up the hill, right? Because our step size is too big. If it's too small, then it takes forever for us to find this global minimum. And so there is sort of Goldilocks step size, which is unfortunately different for every problem that you encounter, right? Which is you sort of find the step very quickly and very efficiently. And so this is, the step size is also called the learning rate, right? As you can imagine, it's like how the rate at which we're learning stuff. And so a very high learning rate and your loss is going to go up wildly like that, okay? A low learning rate, you see how slow it takes. A high learning rate might be like this, and then a good learning rate looks like this, okay? Now, unfortunately, you'll never see this graph. This is just like a hypothetical. The graphs really are very noisy, right? Because the lost landscape, and I don't have a picture of it, it's like mountains on valley. It's like, very cragged, very like rocky, right? And so it's never sort of a smooth one like the one we had before. All right, so let's talk about backpropagation, which is the thing that won the Nobel Prize just a couple of weeks ago. So backpropagation is an algorithm that basically puts everything we've learned together, right? So it's not sort of anything new. So the first step of backpropagation is we need to randomly init, right? So we just find a random place in the landscape, and we'll even talk about how we actually randomly init. There are good ways of randomly init, and then there's bad ways of randomly init, but we'll talk about it later. The second is we make what's called a forward pass, which is a fancy way to say, hey, you have your weights that you already have, and these are generally randomly initialized at the start, right? Make a prediction, right? Based on these weights, see how you go, okay? So that's called a forward pass. You then calculate the loss. So you see how poorly we did, right? Based on that calculation we had before for mean squared error. And then you do what's called a backward pass, which is we update our weights using gradient descent. Okay? So I'll just repeat those 4 steps again. That's actually all there is to backpropagation. So first step is random init. Second is make a prediction based on the weights you have. It might be really crap weights, no problems. Calculate the loss to see how poorly you did. And then update our weights using gradient descent. That's it. Okay? That's all there is to backpropagation. So a very simple formula, but this is at the heart of everything that we've learned so far in AI. Okay? And then step 5 is to repeat it over and over and over again. Okay? You obviously don't repeat the random init constantly, right? You just run random init once, and then you keep on doing a forward pass, calculate your loss, backward pass, forward pass, calculate your loss, backward pass, and you just keep on doing that potentially millions of times. Now, a big question is, when do we stop? So this was something that we were discussing at this table here, which is, and we haven't learned it yet, but generally you always split your data into what's called a train set and then a test set. Okay? So say we have a bar of data here. Say 60% of it is the train, okay? Train, I'm just gonna write TR there. And then 40% of it is test, and we randomly split it, okay? And so when the model sort of operates or learns stuff, it only learns from this one here. So it is never allowed to see the test set. Does that make sense? And so part of the reason why is we're trying to prevent this overfitting, right? It only sees a subset of this data, right? So it only sees, for example, like this point here, maybe it doesn't see that one, it sees that one there. And so it does a really good function, right? And then we have to see how well it does on data that it's never seen before, okay? And so what generally happens is that for the train loss, you'll see this curve, right? So it's always going to keep on improving. But then with the test, at some point, the test will start to diverge, right? Because at this point here, you're overfitting. So that is, the model is starting to learn, instead of this, it's learning this. Okay, so it's fitting too much to this points here. So it's learning it really, really well, but then it's doing poorly as soon as it sees new data. Okay, so one of the ways that we actually prevent this is to detect as soon as these two losses are diverging. Okay, so as soon as it sort of starts to diverge by a certain point here, then it's like, all right, stop the model here. This is the best we can do. Okay? So, yeah.
So, would you ever actually want to find the global minimum? Would that always overfit?
Yeah, so it's actually almost impossible to find the global minimum as soon as you have anything more than free like input features. Because it becomes an intractable mathematical problem. Like in terms of like you need a lot of computational power. And so even just like the house thing, 10 dimensions, how on earth are you going to find the global minimum? Like our computers aren't strong enough to do that. Yeah. So I think if you could, great. But it's mathematically impossible right now. Yeah.
Even if we could, would we want to? Like, would that overfit anyway?
Say that again, sorry?
Like even if we could, would we want to do that anyway? If it's gonna, is it most likely gonna overfit anyway?
You want to find, yeah, you're right in that if it's say the train set, if you find the global minimum of that, it might be an overfit situation, right? So you might not want to. But that being said, from a broad sense, say you had access to all the data in the universe that you could possibly see, if you can find the global minimum of that, then that would be the perfect algorithm, right? Yeah.
Yeah, but we don't use the test, because we use the test set and then we calculate a loss function. Do we do backpropagation using the test set?
So backpropagation is always on the train set.
Oh, no.
It's always on the train set, right? The test is, so remember how we have, say, for example, two curves here, and then one of the steps is calculate loss. You can calculate loss on both the train and the test set, but forward pass and backward pass is generally just on the train set. Okay?
So is it like a simultaneously forward passing through both?
Forward pass is on both train and test because you're forward passing on the whole lot, right? Yeah. But in terms of backward pass and when we're updating our weights, it's only on the train set. Okay. Other questions? Okay. Now backpropagation is cool in that, actually before that, when do we stop? So early stopping is when I was talking about the train and the test losses diverging, right? So that's one way to stop. Other ways to stop that honestly aren't used that much is a fixed number of cycles, right? So that's usually considered a poor option because we don't know how many steps we need to take, okay? The number of cycles are also called epochs. I don't know why, someone just thought it would be funny to call it that, right? And so they're also called epochs. Sometimes it's time or computational limits. So, you have a project due tomorrow and you can't spend the next 5 years trying to optimize this neural network, okay? So sometimes it's that. Sometimes it's when a certain accuracy is achieved, right? Again, rare because, when you're trying to do a medical thing, for example, you don't just stop at 80% because you can try and squeeze out another 5% accuracy, right? And then another is when the loss function just sort of slows down. So it could be that you're sort of reaching a point where it's just sort of like that for quite a lot of time. And it's like, well, do we want to spend another $1 million trying to get this, right? And so you might stop there, okay? All right, now what's cool about backpropagation is that it works for any number of layers, okay? Because it's such a simple algorithm, right? You're just doing a forward pass, seeing how well you did, update backwards, okay? So very cool. I mean, we have, I think, transformers right now, which are a huge number of parameters, huge number of layers, and backpropagation still works. So it's not something that breaks as you continue to scale, which is why, one of the reasons why it's continued to be very popular. Now, is backprop more aligned with MLE or MAP? We actually discussed this before. What are your thoughts? And this is just a recall of what MLE and MAP are. Any guesses? MLE, yeah. I mean, it's just, we're trying to optimize the parameters, right? MAP is much more Bayesian, much more complex, right? And unfortunately, because of that complexity, we don't use it because it's a lot more computationally expensive, right? But that being said, it could be that in future, if we have really cheap computational effort, we could switch to MAP, right? And it could be that MAP is actually where AGI lies or real intelligence lies. It's unclear. Okay, so how many layers and neurons? So this is always a question that comes up, right? And again, we sort of have similar rules. It's sort of, as we increase the number of layers, right, to some insane amount, say like 500, then the model can overfit very easily. So it's very similar to the polynomial degrees, right? We have too many things we can fine tune. And so the model is very sensitive to just pretty much fitting exactly to the data that it sees, right? And so that's why you actually don't see, neural networks at the very least with hundreds of thousands of layers, right? Because it's very easy in code. You can just change it to 1,000 layers, right? Like it's a single number. But the model then becomes very sensitive to overfitting, okay? And so the sort of rules of thumb is that a moderate sized neural network is around 10 to 20 layers. Deep is 20 to 50. And if you're operating sort of above 50, it's like, well, like, what are you doing here, right? Like, are you sure you want to sort of operate that much, right? So it's sort of like having, again, lots of degrees, like 100-degree polynomial function. Okay, so it's a bit of overkill. The number of neurons, because mathematicians like their powers of 2, are generally these numbers here. Okay? And then realistically, most people just sort of mirror architectures that work. Okay, so generally people will just read the literature, they'll read that, I don't know, like the UNet or something works really well for images, like radiology images, so they're just going to copy a UNet and then just do that because it's a safe bet. Okay?
What about the width of each layer? How is that determined?
Yeah, the width of is this one here. Powers of 2.
But so each layer?
Each layer it's like 32, 32, 32, that sort of thing. Yeah. I've seen up to 2,000. Again, it's issues of overfitting, right? So if you have lots and lots of neurons, sometimes it just overfits, right? So again, you generally see for simpler tasks, like sort of here, for more complex tasks sort of here, anything beyond that seems to be overkill, right? Like you're not going to squeeze out more performance.
Is it consistent between, like for one neural network, will it always be consistent with the number of...
It doesn't have to be, but because people like consistency, yeah. But there's no reason why it has to be. Yeah.
So it's like every layer has the same number of neurons.
Yeah. Sometimes it also flares out, right? So, and it's actually in the next slide here. Or it could be more at the, yeah, I mean, it's all theory as to why sometimes it's more or less, that sort of thing. And in terms of thinking about the theory, so say your input is a chest x-ray. At the start of the neural network, it deals with low-level features. So what that means is it'll deal with like an edge, or like this is what an edge looks like, right? And then mid-level is, oh, like it's an edge, like these are all edges together, right? And then at the end here, it's like, oh, like these edges form a lung, right? And then these edges form a heart, okay? So at the start is when it deals with low-level features, and at the end is when it deals with high-level features, okay? So for example, like real shapes in this chest x-ray, right? And so people might theoretically increase the middle because, you know, they want more emphasis on the mid-level features. They might, for example, increase or decrease the high-level features because they want more or less emphasis on these big shapes. Okay, so it's again, it shows just theory. I don't know if it actually works any better, right? But that's sort of the thinking behind when people shape these neural networks. Okay, other questions?
So
Yeah.
So the different layers, are they given particular tasks, or are they naturally?
They naturally
emerge.
Yeah, they naturally emerge from that. Yeah. So it's sort of interesting, right? I don't know why. It's just, yeah, the earlier ones, they learn the lower level features. And then the later ones sort of learn what, like they might detect what the heart looks like, or what the spine looks like, what the lungs look like. They're sort of dealing with high level features. And it's sort of something that just naturally emerges when you train these neural networks. So it's sort of very unusual. And is it how we work as well? I don't know. I think there's parts of the brain that seem to deal with low level edges and stuff, right? And then later down the track, it's like, oh yeah, it's a heart, right? Like that's what we're seeing in aggregate here, right? Interesting. Okay, neural networks and code. So there's two main frameworks you're going to see, right? The first being PyTorch, and we're actually going to be using PyTorch more so. This is excellent for research and testing. Okay, so if you ever join a research lab or whatever, they generally all use PyTorch. Okay. And part of it is because it's very flexible to test different things. So it's built for like experimenting, right? If you want to experiment with this, it's really easy. It's dynamic computation. So that is when you change like a neural network on the fly, it will just continue to backprop through your new neural network, right? So it's not like you have to define it, establish it, and then you have to rerun the whole thing, right? It just changes on the fly, so very cool. And it's a lot simpler to use and learn. And obviously less powerful as you can imagine, right? Because it's built for research purposes. The other one that's used in production, so if you ever work for an AI company, right, like that is actually deploying stuff, TensorFlow is what people use. It's from Google, right? And it's excellent for deployment, so very efficient. Obviously a lot more effort to set up, right? Because it's so efficient. It's static computation, so that is as soon as you define a neural network, you cannot change it on the fly, right? You cannot, like as soon as you deploy it, you have to start from scratch if you intend to deploy a different one. It's obviously a lot harder to learn, but more powerful. Okay, so those are sort of the two packages you'll see. So yeah, so that's if you work in industry, this is if you work in research. So we're going to be using PyTorch. Okay, so what do neural networks actually look like in code? It's actually a little bit simpler than you expect. And so it's just the 4 steps of backpropagation. So step 1 is you randomly init. And then say, for example, we will run 500 epochs of something. You'll do a forward pass, which is you predict, calculate your loss, and then you backward pass, which is you update your weights. Okay, so again, very simple. So let's go through each step. So step 1 is you randomly init the weights. And now you might actually see this done many different ways, okay? So the way that I've put on the slides here isn't the way that everyone always does it constantly, right? Like there's like, it's code, right? So you can achieve stuff in many different ways. It's just a way I particularly like, right? And so how you sort of randomly initialize it, and actually even before that, is you need to import all the PyTorch stuff, right? Like just standard imports. And then you need to define the model parameters, okay? So in this case, we have, say, like an input layer of 10. This is just 3 layers, so the input layer has 10 neurons. The hidden layer has 20 neurons, so we sort of flare out there, and then the outputs is 5, okay? I think it might be slightly different in the code that you get to play with later, but this is what's sort of on the slide here. And then to randomly init, and this is a poor way of randomly initting, but it's sort of what we'll start off with here. you basically just get Torch to randomly create a number of weights where this is the input layer and this is the output layer. Okay, so remember before we had like a free between the input and the output, it's 3 times 3, right? So it's 9 weights you need to init. And so it just does it automatically for you, right? And it also accounts for the biases down here, okay? And so the biases are attached to the hidden layer like we were talking before. We then pass these set of weights to this nn.parameter. And it's a special function that basically says to PyTorch, hey, this is a weight, you need to update it later. You need to like keep track of it, you need to constantly be updating it, okay? And so say for example, you wanted to, I don't know, like randomly init and then like not update this for some reason, right? Like maybe you want to sabotage your group's project, I don't know, right? Like this here, you would basically get rid of an n parameter and then it would not update those weights ever, okay? Okay, so this is another sort of important thing. Hopefully you've learned about the concept of seeds before. Is that right? Have you covered seeds yesterday? Hands up if you know what a seed is. Seeds? Okay. Okay, I'll cover it again. So when you're dealing with code, sometimes there are random things that happen, right? So say, in this case, we're randomly initializing this. When you're trying to figure out how well it's working, the randomness can be very confusing, right? Because as you can imagine, you're getting different stuff every single time, right? And so one of the ways that coders basically get rid of that randomness is through what's called a seed. Okay, so the seed basically forces randomness, but it's the same randomness every time, right? As in like you're getting the same output every time. Okay, so it's sort of like if I have, a coin that I'm trying to toss, heads or tails, right? I can't do this in real life, but in code, I can force it to always be a heads, right? And then I can change the seed, and then it might always be a tail. Does that make sense? And part of the reason is because in code, we actually can't get real randomness, right? So it's something called pseudo-randomness, which is we actually force randomness, right? And in the process of forcing that randomness, it means that we actually can control it. Okay, it's super weird, right? And as an aside, like if you want true randomness, you actually have to attach it to the real world in some way, right? So there's like a famous set of lava lamps in the US, right? In Cloudflare, where they actually detect the amount of light on the lava lamp. And that actually controls like all the crypto stuff, like crypto security stuff that you actually see in the world. Okay? So that's like one way to actually get true randomness, which is you connect it to the real world and it inputs a random number to the computer. Okay? But say you couldn't access the real world in any way, randomness is always forced. Okay? So it's called pseudo-randomness. Okay? So again, a very interesting thing. How it's useful for you is that when you're trying to debug this neural network, right, and you're trying to write something, having this extra line here basically means that you randomize the same numbers every time, right? Randomize every time, right? And so therefore it's easier to debug because you're getting the same result every time. And so you know that the bug you're seeing is not from randomness. Does that make sense? Okay, so it's sort of a neat trick to have. All right, so what does a forward pass look like? Quite easy. So it's actually just the equations that we saw before. So hidden layer, or H, equals the input data, right? Dot product or matrix multiply by W1, right? And then plus the biases, okay? And then the output layer equals hidden layer times by W2 plus bias 2. So it's just those equations we had before, okay? And if you have 3 layers, then you can add a third equation like we were discussing before, 4th layer. Above 10 layers, you don't want to be creating this all manually, right? So there are other ways to do so a lot faster, okay? But for now, you'll just play around with sort of a small number of neural network layers. Okay, step 3 is to calculate the loss. You've seen this before in the regression, right? We just basically use mean squared error, and it's usually a single line. You give it the vectors of the output predictions and then the ground truth, right? And then it calculates a loss for you. That's it, okay? So again, a very simple function. And then finally, you do the backward pass, which is the most complex part of the code, right? And you basically just calculate the loss, you update your weights, you update your biases, and then you clear the gradients for the next run. And then it automatically does the rest, okay? So again, sort of very simple code. So this backward pass is the most complex part of the code, Okay, and that's actually it. That's your first neural network. Any questions? So again, neural networks aren't that complex, you see? It's all sort of basic if you break it down into its constituent components. All right, so move on to the next exercise. Just see what time it is. Actually, you want lunch now or you want lunch later? It's sort of around almost 1 now. Any preferences? Okay, why don't you have lunch now and then you can come back and then do some work, okay? Cool. All right, so let's come back at 1:45. Okay, perfect. So I hope you had some fun dealing with neural networks. So now we're going to talk about how you can change the neural networks and the sort of different things you can actually modify about the neural network, right? Should I use the microphone to spare my voice? Okay, so we're going to be talking about activation functions, loss functions, gradient descent, and weight initialization, and hopefully these terms are now somewhat familiar to you, right? So activation function is the function that we actually use in the node of the neural network, right? And so you were experimenting with ReLU. That's like a classic example of an activation function that is still very, very widely used. Loss functions is, mean squared error, but that works great for continuous outputs, but not so great when we're needing a yes or no answer or, multi-class answers. And so we're going to talk about what that looks like. Gradient descent itself, the one that you're using right now, as you might notice, is quite inefficient. So we're using a very small data set, but you need it to take like 5,000 steps sometimes to get there, right? And so what are better ways for gradient descent? And then finally, weight initialization. Again, we've just used random numbers, but it actually isn't as efficient as a couple of other methods. And so we'll talk through what state of the art on this looks like. Okay, so let's talk through activation functions. And just in terms of time, I suspect we'll finish up to loss functions today, and then tomorrow we'll get started on these last two here. Okay, so activation functions. So these are the functions that are applied at each node. Okay, so after you do the linear combination of the weights and the features, right, you then have to apply some sort of function to it. And like we said, the sort of goal is to have a non-linear sort of activation function, particularly for the hidden layers. Okay, we sort of need a non-linearity there. Now, these don't have to be the same across all nodes. So you can actually go wild and have a different activation function, for all the nodes. That would probably drive your co-workers mad, right? Because it's really impossible to actually follow what you're doing. So usually we have one activation function that's standardized across all hidden layers, okay? And then another special one specifically for the output layer, okay? And the output layer one is a lot simpler because it's dependent on what the output you want, okay? While activation layer is generally something we're looking for with nice mathematical properties, okay? We'll go through what those properties are. So far, like I've said before, we've focused on linear activation functions, but it only gets interesting once we add a non-linear function, right? Particularly for the hidden layers. And the reason for that is the universal approximation theorem. So let's discuss the activation functions firstly for the output layer. Okay, so these are the simpler ones. They're based entirely on what output you want. So for a continuous output, it actually isn't that complex. We have already learned it. We just basically use a linear activation function, which means that we apply no special function on top of what we already have on the code. Okay? So this here is an example of a linear activation function. So we just simply dot product the hidden layer with our weights and then add the bias, and that will provide a continuous output. Okay, so no sort of real change there. In code, sort of do nothing extra. Actually, before this, examples of this that you'll see is things like predicting the blood pressure or hemoglobin or house prices. So anything where you sort of have a continuous value. Now, a big question and a big thing we have to use in medicine is binary outputs, right? Whether someone has or doesn't have a disease. So for example, does this chest x-ray have pneumonia? Is the patient improving or deteriorating? And the two sets of functions that we use for this are sigmoid and hyperbolic tan. Okay? So when do we actually use either one? So sigmoid is used particularly when you need a probability. So that is, you're trying to output a probability for something, right? So it could be, for example, a probability of pneumonia, right? So you want to use sigmoid for that. Or the output itself represents the presence or absence of something, where 1 equals presence and 0 equals absence. Okay, so for example, if I want to say that this chest x-ray, or build a model that says whether this chest x-ray has pneumonia, sigmoid would be my go-to choice, because it's like the patient does have pneumonia, right, which is a 1, or they don't have it, which is a 0. Okay? Tan H is a slightly different function. They look very similar though, which is why they're both used for binary outputs. And it outputs any number between -1 and 1. And so it's generally used for cases where 0 is a meaningful neutral point. Okay? So if we take a look again at that chest x-ray pneumonia, 0 doesn't really mean much, right? Like it's like the patient sort of half has pneumonia, but then half doesn't, right? But for something like the patient is improving or deteriorating, 0 just means that they're stable. So it does mean something, okay? And so if, for example, I'm building an AI model where I'm trying to predict whether the patient is improving or deteriorating, then Tan H would be my preferred output. Does that make sense? Okay? So sigmoid and Tan H are both great choices. It depends primarily on the output that you want. Now, why are they great choices for binary? So they're very similar to that logistic. So sigmoid is a different name for the logistic function that I was talking about. And basically, it squeezes the output to either a 0 or a 1. Okay, it forces the output to be one or the other. And so it's a very sort of useful function to have at the back of our pockets. And so if you ever see a binary output, these are your go-to functions. Now, part of the sort of things that we've learned from actually dealing with these functions for quite some time is that it does require a defined threshold, okay? And usually people just sort of put a threshold at 0.5. But I sort of invite you to actually think more carefully about this if you ever work with this, because sometimes the threshold you set might completely change the behavior of the AI. Okay? And so let's go through what that actually means. And actually before that, this is what it looks like in code, right? So again, very simple. We have here our neural network, right? So a very standard one. And just before the output layer, you just basically apply either the sigmoid function or the tan H function to the prior layer. Okay, so again, very basic in code. Now, thresholds have been something that we've been really poor at, honestly, in medical AI, for the last 10 years. So sort of maybe just to think about this, usually the threshold we set is at 0.5, so that is if the sigmoid function outputs something above 0.5, then we say, yes, this patient has pneumonia. And if it outputs something below 0.5, then we say this patient doesn't have pneumonia, right? Now, what happens if we set the threshold at something higher, like 0.7 or 0.9? So maybe just think about that, and would love to hear any suggestions. Yes, exactly. So it needs to be more confident before it says that this patient has pneumonia. Okay? What about if we set the threshold at 0.3 or 0.1? Yeah, it just says everyone has pneumonia.
Does this tie into like sensitivity and specificity? So like if you have 0.3, then it's super sensitive. 0.9 is like super specific.
Yeah. So it's related, right? In terms of like, it's a bit of a spectrum between it's trying to maximize one or the other, right? Sensitivity or specificity. And so as you can see, setting the threshold changes the behavior of the AI completely, right? And so thinking about thresholds is something you need to, again, it's an assumption, right? It's a human assumption we're trying to impose on this, right? There are methods that we'll cover, I think tomorrow, that actually provide some guidance about how to think about the threshold, but it's not perfect, right? And a lot of these systems, because they're designed by AI engineers, right? As an engineer, you're like, well, who cares? 0.5, it's the easy sort of middle of the road option, right? But it has sort of massive impact as a clinician when you're actually using these systems, right? Because these systems here, as you can imagine, they're sort of flagging red every single time you're using it, right? And probably incorrectly as well. Well, these systems here, you might actually miss something, right? Because the model needs to be really confident before it tells you that the patient has pneumonia, okay? So again, sort of very tricky sort of place to be in. All right, so what happens if you have multiple outputs? So this is a very sort of common problem. So say, for example, you want to ask if someone has, what differential diagnosis they have. Is it, A, B, or C, or D is another sort of type of multiple choice question, right? And so in this case, we need to use a function called the softmax function, okay? Softmax, I was trying to figure out why it's called softmax, and it's a really sort of complicated reason, right? It's like a softer version of an argmax function, and I was like, okay, that's too complex. But it's essentially just a generalization of the sigmoid to multiple outputs. Okay, so it mathematically almost reflects a sigmoid, but for multiple outputs. Okay. Now, how it sort of works is that you basically get raw scores for each category. Okay, so say it's like, does the patient have pneumonia? Do they have heart failure? Do they have blah, 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 right? So you get raw scores, and then you normalize it, and then turn it into a probability. Okay? And they do so with an exponent as well, just to smooth out the function. And then what you sort of need to know is that it always spits out a probability, okay, based on how high these scores are. So you can see here, for example, like the category that got 5.1, it's a 90% probability, okay, because it's the highest value. 2.2, it's a 5% probability. And lower numbers, even lower probability. Okay, so it sort of just smooths out the function and then converts it to a probability. So that's all it does. Now, these, and you might actually see this word around, and I've seen it, I never saw it before a few years ago, but recently I've been seeing it a lot. So it's worthwhile knowing. These are called logits. Okay, I've got no idea why, and you can look it up, and I'm actually not quite sure why, but they're called logits. Okay, so if you ever see the word raw logits, it basically just means the raw scores that come out of the model, right? And this has no meaning in probability. You have to use softmax to get a probability. Okay? Now, why softmax is very important is that it actually is used very extensively for large language models. Okay, so when, for example, you have this sentence here, the boy went to the, you have to use softmax to get probabilities on what the next word is. Okay? So for example, it could be with very high probability that the next word is playground, or the next word is school, or whatever, right? So these are used very extensively in large language models. So this is not going to be the last time you see softmax. You're actually going to see it everywhere. Now, how do we do softmax? Again, very simple. You just go func softmax and then multiply it by the weights and the features. Okay, so that's actually it for output activation functions. Very straightforward, right? So it depends on the output. If it's continuous, then you just use linear, which is add no further function, so you don't change the code. For binary, you either choose sigmoid or tanh, and then for multiple, you just use softmax. Any questions? That's it for output activation functions.
Does softmax's probability always add up to 1?
Yes.
So I know, like, for the case of the boy went to, and then you need to put a word.
Say that again, sir.
The boy went to, and then you want to put a word.
Yes.
Right? So it has to output a word. But like for the example you given, like of diagnosis A, B, C, and D, like
Yes.
it's not capable of outputting no, it's none of these.
If you provide it as an option, maybe.
So only if you put it as like
Yes.
equals. Okay.
Yes. But keep in mind for words, right?
Wait, how?
It's like millions of words, right?
Yeah. And how does it decide like when a sentence ends? Like at some point it has to.
Yeah. So the period or end of, like we actually use an end of sentence token, right? Is one of the options.
Okay.
Yeah. Yeah.
So like the probability of like how to complete the like after one word, what's the word to come after the next word is like you train it, and then they will just store like every word have like probability like after this word.
Yes.
Is it?
Yes.
So when you test it, they will find the word with the highest probability after that.
Not always. It will have a probability distribution, so it could be like playground is first, school is second, you know, nuclear power plant is last or something, right? Like, but then what it does is it actually samples it randomly from the probability distribution that you give it, right? And that's a setting in large language models called temperature. So you can actually, and you get to play with this like next week or week after, but you actually get to play around with the temperature. So you can ask it to choose words that it's less likely to choose, right? And you can try it, and it spits out like almost nonsense, right? Because it's like I tried it, and it started like the end of, you know, the next word that it picked was a Spanish word, right? Like it's and it just then became gibberish after that, right? Because it was like I've never seen this before, and then it just kept on picking really random words. So you can actually increase, you know, how likely it is to pick unlikely words, right? Or you can force it to pick always the highest probability word. And that's actually really important, and why we're teaching it to you is in medicine, you want it to trend towards that, right? In terms of picking reliable words. Yeah, anyway, it's something you'll get to play with, and you'll see like all sorts of gibberish come out of large language models. Yeah.
Spanish, does that mean like with the actual language model, it's like in its dictionary, like all the where
Yes.
you can have like multiple languages as well. Does it have like all the languages technically actually in there, like stored?
Yes.
Okay.
Yes. Yeah.
So every word from every language.
Yeah, it's sort of different because, and you'll learn about this next week, but we don't use words, we use tokens, tokenized versions of words, and usually they're subwords. It's like, you know, the word untrue will be like and then true. So it sees the word untrue as two words, right? Or two tokens rather, right? And so like we would pick like a Spanish token, then pick like a mathematical token, and it's just complete gibberish, right? Like to you it looks like complete gibberish, right? But from its perspective, it sees it just as tokens, right? Like everything it writes is just a bunch of tokens. Yeah. Other questions? These are great questions. Yeah.
Well, just coming back to the classification with pneumonia, why not just issue a probability? Why classify yes you have pneumonia or no you don't?
Because it's the model's never fully confident, right? Yeah.
Right. So why not just say 70% chance of pneumonia?
Well, the better thing is it's like 70% chance of pneumonia, but then 20% chance of heart failure or something, and then 10% chance of that. So it's just how they've constructed it, because that's a more useful, it's called like soft distribution. It's a much more useful thing to be working with. Yeah. Yeah. Other questions? Okay, so let's move on to the hidden activation function. So this is a little bit more complex, right? So this is the list of stuff that we're looking for an ideal hidden activation function, right? So the first is that it should be nonlinear, right? If it's linear, then we're only mapping linear stuff, right? We don't really want that. It needs to be differentiable everywhere, right? Ideally. Now you actually learn about this, some of the functions, they aren't differentiable everywhere. They're not differentiable at a specific point, right? Like say for example 0, right? But because, when we're dealing with numbers, you never get exactly 0, right? Like if you're dealing with like decimal point numbers and I ask you to choose a random decimal point number, the chance of you getting exactly 0 is actually 0, right? It's literally 1 over infinity, because there's an infinite range of numbers between, for example, 0 and 1, right? And so you never get exactly 0, you never get exactly 1. So differentiable everywhere is actually something you can relax, because as long as it's mostly differentiable, the vast majority of numbers, you're fine, right? Because you'll never get exact numbers. Needs to be computationally efficient, so as simple as possible, right? Like we're doing this every single time we're running an epoch, right? And so even if it takes like a second more or a millisecond more or something, it adds up once you run it 1,000,000 times, right? Ideally, it should be zero-centered, so that is, it balances the positive and negatives, right? That is a bit more of a relaxed one. If there's some sort of symmetry around the 0, it's a nice to have feature, but it's not a must have. And then ideally it needs to be non-saturating. And so we'll go through what that even means. But if you think about sigmoid, right? And we actually, I think, go through this in the next slide. Sigmoid looks like this. If you're sort of at like the gradient here or here, you don't get to move very much. Right? Like you're thinking about taking a step and you need to rely on the sigmoid function. When you're at the extremes of the sigmoid, either positive or negative, the gradient there is near 0, right? And so you actually are forced not to move very much. And you can actually mathematically show that you move pretty much nowhere with sigmoid and time once you push past those limits, okay? So, sigmoid logistic function, like I said, this was actually the earliest activation function that was proposed by Hinton, right? So Hinton's the Nobel Prize winner. He was the one who created all this, right? It's non-linear, which is great. It's differentiable everywhere, so no issues. But it has a lot of serious issues. So firstly, it's not zero-centered, sure. Computationally expensive. So that looks like a simple formula, but to calculate the exponent of this is not something that you sort of be wanting to do like millions of times, right? You can, for example, use like a lookup table or something just to sort of help you, but again, it's not very precise, right? And so it's sort of a bit of a nightmare to deal with. It leads to saturation at the extreme. So if you're trying to calculate the differential of this to take a step in gradient descent, when you're here and you're here, this actually zeroes out how far you can step, right? So at some point, you're basically taking no steps, and it's not from the step size, it's from the differential of your loss, right? Where if you remember that formula, the delta of L actually starts to decrease massively, right? And so therefore, you're not taking much steps. So not a great function. Yeah.
So like these kinds of, I think would you say these are asymptotes? So then is having like an asymptote like a good thing or like a bad thing?
It's a bad thing. It's a bad thing. It's a bad thing in both ways. If the asymptote is 0, right, you're taking no steps, so that's called a vanishing gradient. And if the asymptote is vertical, then it's called an exploding gradient because you're now taking huge steps, right? So asymptotic behavior is not good.
Okay.
Yeah, for horizontal or vertical asymptotes, right? It's okay if it's like y equals x asymptote or something. Yeah. Yeah.
Output in the hidden layer, the asymptotes, but okay in the output.
Yeah, okay, output layer is separate. Yeah, so output layer is just dependent on what you want as the output. The hidden layers, you don't want any vertical or horizontal asymptotes. Yeah.
Is that because when you do the derivative of the activation function,
Yes.
is that why? So now that component will become 0, so when you multiply it out, it will...
Yeah, it'll vanish out.
Yeah,
It
yeah.
just basically zeroes out. And if it becomes infinity, then
Then it's the same.
you're taking a huge step. Yeah, it's the other side of the problem. Yeah. So your step really becomes massive or small, right? And you don't want either one, as you discovered. Okay, so the next sort of proposed function in the 1980s, this is 10 years later, was hyperbolic tan. I don't know why they were obsessed with sigmoid and hyperbolic tan back in the day, right? So nonlinear, differentiable everywhere, zero-centered, awesome. Well, the issues, this is not a great function to try and compute every single time, right? It's even worse than sigmoid, right? Saturation at the extreme, so exact same problem, and then limited gradient output. So you can only really do a gradient around here, and it makes sense, right? Sort of here it gets 0, and here it gets 0, so quite bad as well. Okay, so this leads to what I was talking about before just then, which is we have vanishing gradients, or the next one is exploding gradients, right? And so this is some of the math behind it. So if we take a look at this function here, recall that we're basically adding a function, an additional function on top of this one, right? And that's like sigmoid or tan h or whatever. And so at some point we need to actually differentiate this thing, right? So that's number one. Number two is if we're around here, when we differentiate it, it becomes 0, right? And so this leads to the problem of vanishing gradients, right? If we're using sigmoid or tan h and we push these values to the extremes, then we're basically taking no steps in the gradient descent algorithm. Okay, and that's actually one of the reasons why, you know, neural networks, it was promising, but nothing happened in the field because we couldn't figure out how to solve this. Okay, and then the opposite problem happens when we have, you know, like I'm sure someone's proposed the exponential function instead. When you push it here, then it vanishes, but then when you push here, the steps get really large. Okay, so and the model just becomes like, you know, nothingness, right? You just go to infinity every single time. Okay, and then someone, and I can't recall who, realized that we should use this function here, the rectified linear unit, or the ReLU unit. Okay, so that's what it stands for. Widely used, still used today. Okay, all neural networks should be using ReLU. Okay, transformer architectures, which are the more complex versions now, don't use ReLU. They use a more nuanced version of it. Okay, but the sort of structure is still there, and I'll show you what it actually looks like. ReLU is computationally very cheap, okay? So what it basically says is that if you have a negative value, it zeroes it out, okay? So as soon as your weight or your whatever the input is negative, it becomes 0. Otherwise, it's the same value, okay? So that's all ReLU says. Now there is less saturation. Now there's less saturation because we have this whole section here where there's no saturation. But what do you think happens in this section here? So what's the gradient here? 0. Okay? Do you remember? This is basically a horizontal asymptote, right? It's not really an asymptote, it's just on the line, right? And so there is a problem called the dying ReLU problem, whereby the weights keep on getting stuck around here, and then it's taking no steps on for those weights. Okay? So again, you see the intuition there? ReLU is not perfect either. Okay? Now ReLU itself is not differentiable everywhere because you can't calculate the gradient here, right? Like at exactly 0. But not a massive issue because we're dealing with floating point numbers or decimal point numbers. And so because of that, you never get exactly 0. You never get exactly 0, right? The probability of that is 0. Okay, and it's also not zero-centered, which again, we sort of just ignore a little bit because otherwise the function is great and we can't get everything that's perfect. So what are the issues? Dying ReLU, right? So the weights can sort of get stuck there and then you sort of never move along, right? And sometimes you can also get exploding gradients because at some point here, if you keep on going up, it just keeps on going that way. And so the step size actually never ends up decreasing, right? You sort of always just get the same step size every single time. And you know, when you're at sort of at the bottom of the valley, you don't want to be taking the same step size, right? You almost want to take smaller step sizes as you're getting near the bottom of the valley, okay? All right, so someone looked at this and they were like, okay, instead of this 0 gradient that we have here, can we actually do a very small gradient that looks like this, okay? And so this is called the leaky ReLU. Leaky because some information leaks through here, okay? And so it solves the dying ReLU problem, right? And usually this gradient is 0.01. Okay, so that's called a leaky ReLU. You'll see that around. Is it still used as much anymore? I don't know. Most people just default to the ReLU. Okay, is it clearly, I think theoretically it's better, but practically it doesn't seem to improve much. Now you guys seem to sort of be getting this, so I'm going to get to some of the more advanced stuff. So the intuition, if the alpha is too small, it might lead to vanishing gradients anyway. All right, so someone was like, all right, can we actually make alpha, which is the gradient of this component here, a learnable parameter, okay? And so that's called parametric ReLU or PReLU, okay? And what happens here is that it removes any assumptions from leaky ReLU, which is setting the gradient of this, but it makes it a trainable parameter. So it's something additional we need to train on top of the neural network that we already have as well, okay? And some of the guidance around this is that generally you don't want to train you want to train as little as you can, right? In terms of you want to train just the neural network and not all these other numbers as well. But sometimes those additional numbers add some flexibility that might really help with training the model, okay? So there's always sort of trade-offs. Someone else suggested, hey, can we use an exponential function for this component here? So that's called ELU, okay? Exponential linear unit. So again, just different ideas around in academia. This here is computationally more expensive because now we're reintroducing an exponential term we need to calculate every time, right? It requires a tunable parameter. So there is actually a value that we need to tune or train. And it can sometimes lead to exploding gradients on this section here. All right, and then the final one that we've finally settled on for transformers is something called the Gaussian error linear unit, or the GLU. Okay, people like their ELUs in AI. And this is best practice for large language models and transformers, okay? So if you're gonna ever train a transformer, a large language model, you just use the GLU. You don't have to know fully how it works, but this is what everyone uses, right? And how it works mathematically is that it multiplies the ELU with a Gaussian or normal CDF. Now, do you remember that the PDF of a Gaussian graph looks like that, right? So CDF is the cumulative version of it, right? And so it looks like that, right? What we have here. Okay, does anyone, do you remember PDF, CDFs, right? Right, so this is the Gaussian CDF. Now what does this mean, or what's the impact of this? And this is actually what the GLU ends up looking like, right? It looks pretty much like the ReLU, but it has this little, this little dip right here, okay? Now, what does it mean? So positive values are completely preserved, so the positive values are treated very much in the same way, okay? There is a smooth transition at 0, so there's no sort of issues of differentiability or anything like that. Low negative values are partially retained, right? Because there's a little bit of weights that can get through here, okay? And then high negative values are completely lost, so it's very similar to what we had before, okay? And so I think I have a next slide which explains why it's good. So why does it work well for large language models? And this is all in theory, right? No one's ever proven this, but this is why we think it seems to work well. Words require a lot of nuance. The smoothness allows that nuance to be captured. I feel like I'm selling an ad, right? Small negative values do pass through, and that's really important when you have extremely deep neural networks, which is what we have in transformers, okay? So that's the GLU. Okay, so how do we actually apply it? Again, very simple, right? So we have the hidden layer there. You just add func ReLU or func JLU. Okay, so very, very straightforward. Okay, and so that's actually it for hidden activation functions. Use the ReLU for neural networks. That's the standard. That's the gold standard right now. And then for transformers, use the JLU. Okay. And I've just added the Nike swoosh there because someone actually, or swish there because someone actually created a Nike swish function, but it never sort of really took off. So just use the ReLU and JLU, okay? All right, any questions before we move on to loss functions? Yes.
JLU. So you said it's multiplying by normal CDF, right? So does that mean like at 0, normal CDF is half?
Half,
Right?
yes.
Yeah, so you're just always multiplying by a number that's less than half, and then the more negative you go, that goes to 0, right?
Yes.
Okay.
Yeah. So there's that little dip there that allows information to pass through, right? Because if you zero it out, all that information is always lost. Yeah. Yeah.
Is that not computationally difficult?
So it's a great question. ReLU is not, right? So it's ReLU multiplied by normal CDF. Normal CDF is actually really optimized in code. And how they do it is they use lookup tables, right? Down to like free decimal point precision, right? And so it's really just pulling something from a lookup table and then multiplying it out. Yeah. Other questions? Awesome. Okay. All right, loss functions. So that's all about activation functions. Now let's talk about the loss function. So recall that loss functions are the error we're trying to minimize, right? It's what we're trying to sort of minimize and just optimize for. Now mean squared error works great for continuous data, but it doesn't work so great for binary and multi-outputs, right? So we need something that almost matches what we have, right? So mean squared error, cool. We're sort of familiar with it. So for binary problems, what we use is a formula called binary cross entropy, okay? Or BCE. And this is the formula for it. And recall that binary outputs are usually a value between 0 and 1, right? Where 1 is we think that this is the case with 100% probability, and 0 is we think it's the case with 0% probability, okay? So for example, if you get an output of 0.6, it means that I think this will happen with a 60% probability, okay? So it could be, for example, does this patient have pneumonia? I can spit out 0.6, okay? And remember, this is separate to discussions of thresholding, right? If we say 0.5 is the threshold, as soon as we have 0.51, it's yes, this patient has pneumonia. Okay, 0.49, no, this patient doesn't have pneumonia. So let's take a look at how this function actually works. Now recall that y hat is what the model predicts, y is the ground truth. If we look at a single sample, right, say our ground truth is 1, right, so that is y equals 1. This whole section here is cancelled out, right, because we have 1 minus 1. Okay, so that 0 is out, it cancels out this whole section. So this formula we now have is just this, okay? And if you graph it, then this is what the loss function looks like, okay? So if I, for example, predict a 0, that's really wrong, okay? But the closer to 1 I predict, the less loss there is, okay? So again, just a very sort of simple formula to be aware of. If we reverse it, say it's a 0, so the ground truth is 0, this will get rid of this whole section here, right? And so we're left with this formula here, and this is what the graph looks like. So again, if I predict a 1 and the answer is 0, I get punished. And if I predict a 0, then there is no loss. That make sense? So it's, again, just quite simple math, right? So that's binary cross entropy. Now, if we have multiple outputs, then we use what's called the softmax cross entropy. Now, keep in mind that softmax cross entropy is different to the softmax activation function. Okay? They're confusingly called the exact same thing, but it's nice because you use the softmax activation function with softmax cross entropy. Okay? So they should always go hand in hand together. But when someone says softmax, you have to ask them, are they talking about the loss function or are they talking about the activation function? Okay? So great for multiple outputs. Conceptually, it's actually almost identical to the softmax activation function. So if you recall, there was this sort of exponent thing happening here, right, to get the probabilities. But we simply just apply a negative log to it, right? Now, does anyone know why we apply a negative log? So negative log is a pattern that you'll see time and time again in AI, right? And it actually composes of two things, the negative and the log, right? Why do we use the log? Does anyone have an idea? Yeah.
Stab, but can you it's because you can minimize it? Like you minimize the negative log and you maximize the log.
You're close. Why do we use the log though? I think you're mixing the negative.
Okay.
Yeah.
It's because the numbers are really small, or like close to zero.
Why therefore do we use the log then?
It sort of like scales it to like an interpretable loss, because
Interpretable loss?
I mean,
Yeah,
is it
maybe.
like-
Maybe,
is it
sort
like
of. Maybe it's related. Yeah. Other ideas? Sorry?
Avoid storing as a really small decimal.
Yeah, so say we have, maybe I'll give an example. Say we have the word, the boy went to the whatever, right? And we have millions of words it could be afterwards, right? Or maybe thousands of words or whatever, realistically, right? What is the probability of like the 1,000th word? Is it a small number or a large number? Very, very small, right? So there's probably like almost like one that's like 30% or whatever, and then it keeps on decreasing. And so there's a very long tail of words. It's like the boy went to the laptop. Like that doesn't make any sense, right? So laptop is near zero probability, right? And so if we have so many values with such low numbers, and that's the sort of like environment we need to operate in, right? The logs make it a lot easier to deal with those numbers, right? Because things like multiplication suddenly become addition to the computer, right? So it basically allows us to deal with really small probabilities, okay? So you actually see log used everywhere, and it's almost an arbitrary reason. It's because it makes it easier for us to deal with these small numbers. Okay, so there's no sort of mathematical reason beyond just ease of use that we need to use log. Does that make sense? And then if you ever see like natural log, it's because log E is one of those things that computer packages can deal with very easily. And so we use log E. We don't use the E for any reason, right? But that's for AI. When it comes to biological things, then E is a very critical number, right? It's almost like the number that drives biology. Okay, so if you ever seen a biology, then there's reasons for that, right? But log E in an AI, like non-biological use, it's merely just because it's easier to use. Yeah.
If it's using small numbers though, isn't it gonna like balloon up to infinity or negative infinity, depending on your
For which?
For log.
For logs?
Yeah, because there's an asymptote x equals 0, right? So isn't that like a problem?
I don't think so. I think it actually makes it easier to handle. It's more to do operations with the numbers rather than like being worried about the sort of asymptotic nature.
Pretty easily is what I'm saying. Right?
Sorry?
It can diverge pretty easily is what I'm saying. But
Yeah,
you mean,
it
like,
probably can. Yeah.
Okay.
Yeah, I agree. Yeah, yeah. So I think there's probably like ways where you have to watch out where it's going, right? But the way that it's used with an AI, at least in terms of the small probabilities, it is easier to use and actually handle. Yeah, you probably cap it. Yeah, yeah. Okay. So always use softmax output with softmax cross entropy. And again, it's a very similar formula. So this is the score for the correct class, and this is the sum of scores for each class, right? And we didn't discuss it, but why do we use the negative? What's the negative for? Any ideas? So it basically just turns this number into a loss, whereby higher numbers, right, just means that you're doing worse, right? Whilst now lower numbers means you're doing better. So it's just more of like a polarity thing. So let's take a look at what these numbers actually mean. So say, for example, the answer is pneumonia. Okay, like it's like what is happening in this chest X-ray? Pneumonia, heart failure, or normal, right? Say the answer is pneumonia, and this is our probability predictions. Okay, so 60% likely that it's pneumonia, 20% likely that it's heart failure, and 10% that it's normal. Okay, the softmax loss that we'll get is 0.357. Okay, and it's just a simple calculation, which is negative log of e to the power of the correct class, so 0.6, divided by all the classes together. Okay, so 0.6 plus 0.2 plus 0.1. Now say, for example, instead, we were very confident that it's pneumonia, so 0.9. So instead, this will be 0.9, 0.9, 0.08, and 0.02. Then we get a lower loss because we were correct. Okay, so you see how it's sort of a neat function in order to deal with probability distributions. Okay, and we actually use this quite extensively again with large language models. Okay, because it allows us to sort of map our probability distributions to the correct ones. Okay, any questions? So softmax is particularly complex. Okay. All right, so in terms of application, or how you actually write it in code, it's very similar. So we have here MSE loss, which you're familiar with. For binary cross entropy, you just simply write binary cross entropy instead. And for softmax cross entropy, you just simply write cross entropy. So you don't even need to call it softmax. Okay? So again, very, very simple to change. All right, so in summary, for continuous outputs, mean squared error, binary outputs, you need to use binary cross entropy. And then for multiple outputs, you need to use softmax cross entropy. Okay? Now, these aren't the only loss functions, right? So we previously talked about cosine similarity as being the backbone of some loss functions. But there are also sort of more general loss functions that I think actually hold the key to really key questions in AI. And this is called the Kullback-Leibler divergence, which is a metric that actually detects how much error or loss there is between two probability distributions. Okay? So again, I don't fully understand the formulas for this yet, but it is conceptually a really important thing for us to understand what is missing from probability distributions, right? And these start to get quite important once you're dealing with things like large language models, because you could have a large language model that, for example, could be trained on this data here, but then reality actually reflects this data here, right? So how do we, actually shift the model so that it better reflects reality? Okay, that's sort of how a lot of AI scientists think about it. Okay, so now let's move on to sort of the last exercise of the day. So let's work through activation loss functions, and then we'll call it for today.